Good evening and welcome to Physic for Sleep. Tonight we embark on an intellectual journey exploring the profound mystery of supermassive black holes, specifically focusing on the colossal Phoenix A and our very own galactic center, Sagittarius A. Before we gently immerse ourselves in the gravitational depths of these cosmic behemoths, I would like to know where you are at this moment. Perhaps you are lying in bed, watching the gentle play of shadows on your ceiling. Or maybe you are wrapped in a soft blanket on a quiet porch, feeling the cool caress of the night air. If these deep reflections help you relax and organize your thoughts before sleep, please support the channel with a like and subscribe so others can find their way here too. Now, just breathe. Allow your eyes to grow heavy. And let's begin. We begin our journey by contemplating the very nature of supermassive black holes themselves. These aren't merely larger versions of the stellar black holes formed from collapsing stars, which are already astonishing in their density and mystery. Supermassive black holes are celestial entities of a profoundly different order of magnitude entirely, pushing the boundaries of what we can conceptually grasp and understand. Imagine, if you will, a region of space-time where gravity is so overwhelmingly intense that nothing, not even the swiftest particle of light, can escape its relentless, all-consuming grasp. Now, amplify that concept to an almost unimaginable scale where the mass of millions or even billions of suns is concentrated into a space smaller than our solar system. Supermassive black holes reside at the radiant, energetic hearts of most, if not all, large galaxies, including our own tranquil spiral, the Milky Way. Their masses can range from millions to tens of billions of times that of our familiar Sun. Yet they are compressed into volumes far, far smaller than our entire solar system. The sheer density within their event horizons is, quite simply, mind-bending, inviting a quiet moment of profound contemplation on the very extremes of cosmic existence and the fundamental laws that govern its majestic unfolding. How these colossal leviathans, these silent cosmic rulers, come into being and grow to such immense proportions remains one of astronomy's most compelling and active areas of inquiry. A puzzle scientists are meticulously piecing together. Theories suggest they likely grow through a complex combination of interconnected processes unfolding over vast cosmic timescales, billions of years in duration. One primary mechanism involves the gradual yet persistent accretion of gas and dust from their galactic surroundings. As this diffuse material spirals inward, inexorably drawn by the black hole's immense gravitational pull, it forms a swirling, superheated disk known as an accretion disk. The tremendous friction and energetic collisions within this disk heat the infalling matter to millions of degrees, causing it to emit prodigious amounts of radiation across the entire electromagnetic spectrum, from radio waves to powerful X-rays and gamma rays. These luminous emissions can often outshine all the stars in the host galaxy combined, manifesting as active galactic nuclei, or AGNs, which serve as powerful beacons illuminating the distant universe. These AGNs provide invaluable clues to the black hole's intense activity and its ongoing growth. Another significant pathway to their formidable growth involves the merger of smaller black holes, perhaps even the grand collision and subsequent merging of entire galaxies, which can funnel vast quantities of gas and stars toward the central supermassive entity, offering it an abundant and continuous cosmic feast, a process of spectacular cosmic cannibalism. Despite their unfathomable mass and profound gravitational dominance, the physical size of a supermassive black hole's event horizon, that conceptual boundary of no return, is still relatively modest when compared to the vast expanse of the galaxy it so powerfully anchors. For instance, the event horizon of Sagittarius AI, the supermassive black hole nestled at the very center of our Milky Way, is only about 17 times the diameter of our Sun. To put that into perspective, if our Sun were replaced by Sagittarius AI, its event horizon would comfortably fit within Mercury's orbit, a mere fraction of the solar system's true scale. Yet, its gravitational influence extends across hundreds of thousands of light-years, subtly dictating the intricate orbits of billions of stars and shaping the overall dynamics of its galactic home. This profound, invisible pull acts as a silent, unseen architect, subtly orchestrating the grand cosmic dance of matter and energy. It guides the formation and evolution of the galaxies we observe, influencing their destinies in ways we are only just beginning to fully comprehend. A quiet, omnipresent force of cosmic order that governs the grand structures of the universe with an almost ethereal touch. Within this extraordinary and enigmatic realm, the familiar laws of physics, as we understand them in our everyday experience, undergo a dramatic and elegant transformation, challenging our intuitive notions of space and time. The event horizon, as we know, is not a solid physical surface that one might touch or feel, but rather a conceptual boundary, a profound threshold of no return from which escape is no longer possible for anything, not even light itself. Crossing this threshold means that all future paths for any object inevitably lead inward towards the singularity, a theoretical point of infinite density where space-time itself is thought to break down into an unknown, perhaps even undescribable state, a realm beyond our current physical theories. From an external perspective, an object approaching the event horizon would appear to slow down, its light gradually reddening and dimming due to extreme gravitational redshift until it seemingly freezes in time, fading peacefully from observable existence, a kind of eternal farewell. This phenomenon is not a trap in any dramatic or terrifying sense, but an inherent and elegant consequence of the extreme curvature of space-time, precisely predicted by Albert Einstein's general theory of relativity. Inside this boundary, even the very concept of direction fundamentally changes. What was once considered forward in space becomes inextricably linked with forward in time, inevitably guiding all matter and energy towards the central singularity, an unavoidable fate woven into the very geometry of existence. This fundamental alteration of geometry is what profoundly defines a black hole's mysterious and inaccessible interior, a place where the cosmos redefines itself. The intricate relationship between supermassive black holes and their host galaxies is a complex and profoundly fascinating narrative of coevolution, a cosmic dance spanning billions of years. Modern astronomical research consistently suggests that the growth of a central supermassive black hole is intimately linked with the growth and development of its surrounding galaxy, a symbiotic relationship that shapes both entities in a delicate balance. Feedback mechanisms, both positive and negative, play a crucial role in this cosmic interplay. When a supermassive black hole is actively accreting matter, the intense radiation and powerful jets of high-energy particles it emits can effectively heat and expel vast quantities of gas from the galaxy. This energetic outflow, sometimes observed as powerful winds, can suppress star formation, acting as a cosmic regulator that limits the galaxy's stellar population by clearing out the raw material needed for new stars to ignite. Conversely, during periods of quiescence, when the black hole is less active and its energetic output diminishes, the gas within the galaxy is allowed to cool and collapse more readily under gravity, triggering vibrant bursts of new star birth. It is a delicate and dynamic balance, a cosmic symbiosis where the colossal black hole acts as both a profound destroyer and a majestic creator, profoundly influencing the environment around it and shaping its destiny. This continuous interaction underscores the interconnectedness of cosmic phenomena, demonstrating how even the most extreme objects contribute to the grand, evolving story of the universe, a testament to its intricate design. Considering these immense, unseen gravitational anchors that command the centers of galaxies, one might pause to reflect on our own tiny, yet utterly significant place within the vast galactic tapestry. Our Sun, along with its family of 8 planets and countless smaller bodies, orbits Sagittarius AOI at a comfortable and safe distance of about 26,000 light-years. This grand journey, a single revolution around the galactic center, takes approximately 230 million years to complete, a timescale that dwarfs our human perception and reminds us of the universe's patient, deliberate unfolding. We are, in essence, an integral part of this grand, slow waltz, subtly influenced by the distant, powerful pull of our galaxy's heart, yet insulated from its destructive embrace. This profound knowledge can evoke a sense of deep interconnectedness, reminding us that even in our quietest moments of rest and reflection, we are continuously moving through a universe shaped by forces almost beyond our immediate comprehension, yet intimately connected to the very fabric of our cosmic home. The very atoms that compose our being are part of this grand, eternal cycle, having been forged in the fiery hearts of ancient stars, dispersed by the spectacular violence of supernovae, and then gathered into planets and eventually living beings. We are forever bound to the unfolding, majestic story of the cosmos, a transient yet conscious configuration of stardust. This understanding invites a tranquil acceptance of our place in the universe, a silent acknowledgement of the cosmic grandeur that surrounds and defines us, allowing our minds to drift peacefully into the deep. Having explored the general nature of supermassive black holes, their formation, and their profound influence on galactic evolution, our journey now takes us to two specific yet profoundly distinct examples that illuminate the vast spectrum of these cosmic giants: the remarkably active Phoenix A and our own galaxy's more serene central black hole, Sagittarius AI. Let us first turn our attention to the distant and truly colossal Phoenix A. This behemoth resides at the heart of the Phoenix cluster, an immense gathering of thousands of galaxies located approximately 5.8 billion light-years away in the constellation Phoenix. What renders Phoenix so uniquely extraordinary is its gargantuan mass, estimated by scientists to be around 100 billion times that of our Sun, establishing it as one of the most massive black holes ever detected in the observable universe. But its sheer gravitational magnitude is only one facet of its profound grandeur. Phoenix A is also characterized by an astonishing level of activity, continuously spewing forth powerful energetic jets of high-energy particles and intense radiation into the vast expanse of the surrounding intracluster medium. These jets are not mere transient phenomena. They are colossal, extending for hundreds of thousands of light-years into space, carving out immense, observable cavities within the superheated gas that permeates the cluster. This relentless outpouring of energy acts as a cosmic heating mechanism, quite effectively preventing the diffuse gas within the cluster from cooling sufficiently to condense and form new stars. It essentially stifles starbirth on a monumental galaxy-wide scale, a profound process known as negative feedback. Such immense energetic output profoundly underscores the understanding that black holes are far from being passive gravitational wells. Rather, they are dynamic, influential forces that can profoundly sculpt the evolutionary trajectories of their entire host clusters, acting as silent yet undeniably powerful architects of cosmic destiny. The sheer scale of this interaction invites a moment of quiet awe, contemplating a single entity's power to shape the fates of entire galactic populations. In stark and captivating contrast, we now direct our gaze much closer to home, to the very serene core of our own Milky Way galaxy, where the intriguing Sagittarius AI quietly resides. With an estimated mass of approximately 4.3 million times that of our Sun, it is a considerably smaller, yet equally fascinating, supermassive black hole. What distinguishes Sagittarius A so remarkably is its relative tranquility, its almost dormant state. While it does occasionally exhibit subtle flares of X-ray emission and other signs of minor activity, it is largely quiescent, a sleeping giant compared to the roaring, energetic output of a Phoenix A. The most compelling and direct evidence for its existence comes from the meticulous observation of the intricate, remarkably rapid orbits of stars, often affectionately referred to as S-stars, in its immediate gravitational embrace. For instance, the star designated S2, a swiftly moving celestial body, completes an entire elliptical revolution around Sagittarius A mass in a mere 16 years. At its closest approach, this star hurtles through space at speeds reaching thousands of kilometers per second. These extraordinarily precise stellar dances, meticulously tracked over decades by pioneering astronomers such as Andrea Ghez and Reinhard Genzel, whose groundbreaking work in this field earned them richly deserved Nobel Prizes, provide irrefutable empirical proof of an invisible, supermassive object residing at our galaxy's very heart. The relatively serene nature of Sagittarius AI offers an invaluable opportunity for scientists to study the intricate dynamics of space-time and gravity in a comparatively calm cosmic environment, thus providing a unique and accessible cosmic laboratory for profound discovery and understanding. The profound contrast between the intensely active Phoenix A and the largely quiescent Sagittarius A beautifully illuminates the diverse and varied lives that supermassive black holes lead across the universe. Phoenix A, a hyperactive behemoth, exerts an overwhelming influence, virtually dictating the star-forming destiny of its entire galaxy cluster, acting as a powerful engine that sculpts its surroundings through its formidable energetic output. Sagittarius EE, by comparison, presents itself as a more gentle giant, a quiet, stable anchor for our spiral arm, its gravitational influence more subtle, yet equally fundamental. This gentle presence allows for the rich and intricate tapestry of star formation and planetary development that we observe throughout our galaxy. This striking duality highlights that while gravity is an unyielding, universal force, its specific manifestations at these extreme cosmic scales are wonderfully varied and profoundly complex, intricately dependent on factors such as the ambient availability of fuel, the gas and dust it can consume, and the profound historical mergers of galaxies that have shaped its past. It thoughtfully encourages us to consider how our own galactic environment, characterized by its relatively peaceful central black hole, might have inadvertently contributed to the stable and enduring conditions that were so necessary for life to not only emerge, but also to flourish in our corner of the cosmos. Perhaps within the quiet, almost imperceptible hum of Sagittarius AZ, we find a subtle reflection of the precise conditions that allowed for our very existence, a gentle yet profound reminder that even the most extreme and powerful cosmic forces can, in their own unique and mysterious way, foster the intricate conditions for the development of complexity and, ultimately, life itself. We are, in a very real and humbling sense, living in the majestic, yet mostly dormant, shadow of a truly magnificent cosmic heart. The comparative study of these two extremes, the roaring furnace of Phoenix A and the tranquil anchor of Sagittarius A, undeniably deepens our collective understanding of the universe's grand, evolving narrative, inviting us to ponder the intricate connections that bind all cosmic phenomena together, from the largest structures to our own fleeting presence. Having just journeyed through the contrasting realms of Phoenix A and Sagittarius A, understanding their immense scale and their varying degrees of activity, our thoughts naturally turn to a deeper question. How do we, from our distant vantage point, even begin to perceive such enigmatic entities? Black holes, by their very definition, are regions where light cannot escape, making them inherently invisible. Yet, through ingenuity and persistent observation, humanity has developed remarkable ways to unveil their hidden grandeur and understand their profound cosmic influence, allowing us to piece together their silent, powerful narratives across the vast canvas of the universe. For active supermassive black holes like the distant and energetic Phoenix A, our primary window into their existence lies in the dramatic effects they have on their immediate cosmic surroundings. We cannot see the black hole itself, but we can witness the spectacular dance of matter caught in its relentless gravitational embrace. As gas and dust spiral inward towards the event horizon, they form an intensely hot, swirling accretion disk, a luminous maelstrom of superheated plasma. The friction within this disk heats the material. Astronomers utilize powerful radio telescopes, X-ray observatories, and optical instruments to capture these emissions, which paint a vivid, albeit indirect, portrait of the black hole's activity. The powerful jets observed emanating from Phoenix A, for instance, are not light from the black hole, but rather streams of highly energetic particles, accelerated to near-light speed by complex magnetic fields near the black hole, then propelled outward for vast distances. These jets, visible in radio wavelengths, serve as undeniable evidence of the immense energy being harnessed and channeled by the central supermassive black hole, a testament to its dynamic and transformative power in shaping its galactic environment, acting as a cosmic engine of creation and destruction. In the case of quiescent supermassive black holes, such as our own Sagittarius A, the observational challenge is even greater, as the absence of a brightly glowing accretion disk means we must rely on even more subtle clues. Here, the evidence for the black hole's presence is derived from the meticulous tracking of the gravitational dance of stars in its immediate vicinity. Imagine a cosmic ballet, with stars pirouetting and accelerating at astonishing speeds around an unseen conductor. By precisely measuring the orbital paths and velocities of these so-called S-stars, particularly the star S2, which makes a full orbit in merely 16 years, astronomers can infer the mass and location of the invisible object at the center. This pioneering work, led by luminaries such as Andrea Ghez and Reinhard Genzel, involved decades of patient observation using adaptive optics on ground-based telescopes to counteract the blurring effects of Earth's atmosphere. The extraordinary precision of these measurements has confirmed the existence of a compact, supermassive object, consistent only with a black hole at the heart of our galaxy. It is a triumph of observational astronomy, demonstrating how the subtle yet undeniable curvature of space-time can be revealed through the elegant motions of celestial bodies, providing irrefutable proof of a hidden cosmic giant. Beyond the direct emissions of active black holes and the gravitational tugs on nearby stars, another elegant method for inferring the presence of these colossal objects is through the phenomenon of gravitational lensing. This effect, predicted by Einstein's general relativity, occurs when the immense mass of a foreground object, such as a galaxy cluster containing a supermassive black hole, warps the fabric of space-time around it. As light from a more distant background object travels through this warped space-time, its path is bent, much like light passing through a colossal imperfect lens. This bending can magnify, distort, or even multiply the images of the background objects, creating arcs, rings, or multiple images that betray the presence of unseen mass. While gravitational lensing doesn't directly image the black hole, it provides a powerful means to map the distribution of mass in a galaxy or cluster, allowing astronomers to deduce the presence of a supermassive black hole as a significant contributor to the gravitational field. It is a cosmic optical illusion, revealing the hidden architecture of the universe through the subtle distortions of light itself, a gentle reminder that even the void is capable of profound influence. The pinnacle of direct observation, though still indirect in essence, arrived with the Event Horizon Telescope project. This international collaboration of scientists, utilizing a network of radio observatories across the globe, effectively transformed our entire planet into a single, Earth-sized, virtual telescope. Their ambitious goal was to achieve the angular resolution necessary to image the shadow of a black hole's event horizon. In 2019, they delivered a groundbreaking image of the supermassive black hole at the center of the galaxy, M87, followed in 2022 by the first image of Sagittarius A itself. These images, rather than depicting the black hole, reveal the silhouette cast by its event horizon against the backdrop of glowing, superheated gas swirling around it. It is like seeing the outline of a profound cosmic absence, a dark circle surrounded by a fiery ring. This monumental achievement not only provided stunning visual confirmation of Einstein's predictions in the most extreme gravitational environments, but also allowed scientists to test general relativity with unprecedented precision, observing how space-time is dramatically warped in the immediate vicinity of these cosmic titans. It offers a tangible, if still abstract, glimpse into the heart of a phenomenon that once seemed forever beyond our visual reach, inviting us to ponder the limits of our perception and the boundless ingenuity of the human mind. As we consider these incredible techniques, from observing distant jets to tracking the ballet of stars and capturing the very shadow of a cosmic void, we are reminded of the profound human drive to understand the universe around us. Each discovery, each new image, deepens our appreciation for the intricate beauty and underlying physical laws that govern existence. These supermassive black holes, whether raging like Phoenix A or slumbering like Sagittarius AEI, are not just astronomical curiosities. They are fundamental components of cosmic evolution, silent witnesses to billions of years of galactic history. And in our quiet contemplation of these distant, powerful entities, we find a reflection of our own enduring curiosity, our desire to map the invisible and comprehend the incomprehensible, connecting our fleeting human existence to the eternal, majestic dance of the cosmos itself. The knowledge we gain from these distant observations helps us to understand not only the universe, but our very place within it, a tiny, self-aware part of this grand, unfolding mystery. Yet, even with these remarkable observational triumphs, the enigma of supermassive black holes deepens as we approach the very limits of our current scientific understanding. Beyond the event horizon, where light and information become irrevocably bound, lies the theoretical heart of a black hole, the singularity. This is not a physical surface, but rather a point in space-time where the density of matter and the curvature of space-time become, according to the equations of general relativity, infinite. It represents a profound breakdown in our mathematical models, a frontier where the elegant framework of Einstein's gravity must ultimately yield to a more complete yet undiscovered theory that seamlessly integrates the principles of quantum mechanics. The singularity, in its silent profundity, serves as a humble reminder of the vast territories of knowledge that still await our exploration, a gentle cosmic whisper of the universe's ultimate mysteries. It is a place where our familiar laws dissolve, inviting a contemplation of the truly unknown, a realm where even space-time itself redefines its very essence. One of the most profound theoretical challenges presented by black holes is the so-called information paradox. This fundamental puzzle arises from a conflict between two pillars of modern physics: the general theory of relativity, which suggests that information about matter falling into a black hole is lost forever, and quantum mechanics, which posits that information, in any form, can never truly be destroyed. Imagine, if you will, a book with all its intricate stories and scientific facts, slowly spiraling into a black hole. According to classical general relativity, once it crosses the event horizon, all the unique information contained within its pages would eventually be lost to the observable universe, seemingly vanishing without a trace. However, quantum mechanics insists that such a complete erasure of information is impossible. It must, in some form, be preserved, even if scrambled beyond recognition. This paradox has spurred decades of intense theoretical debate and research among physicists, pushing the boundaries of our conceptual frameworks and urging us to seek a deeper, more unified understanding of how gravity and quantum reality truly intertwine at their most extreme intersections. The resolution of this paradox, scientists believe, may hold the key to a grander theory of quantum gravity, revealing a more complete tapestry of cosmic law. Adding another layer of subtle complexity to the nature of black holes is the remarkable theoretical prediction of Stephen Hawking that black holes are not, in fact, entirely black. Through a fascinating quantum mechanical effect occurring at the event horizon, black holes are believed to slowly emit a faint thermal radiation, now famously known as Hawking radiation. This radiation arises from quantum fluctuations in the vacuum of space near the event horizon, where pairs of virtual particles and antiparticles are constantly popping into and out of existence. Occasionally, one particle from such a pair falls into the black hole while its partner escapes into space, carrying a tiny amount of energy away from the black hole. Over unimaginable timescales, far exceeding the current age of our universe, this continuous, gentle emission of radiation would cause black holes to slowly lose mass and eventually completely evaporate. For a supermassive black hole like Phoenix A or Sagittarius A, this process is incredibly slow, a cosmic eons-long whisper rather than a dramatic explosion. It is a subtle yet profound illustration of how quantum mechanics can gently influence even the most monstrous gravitational entities, suggesting that nothing in the universe, not even a black hole, is truly eternal, but rather participates in an endlessly slow, graceful dance of transformation. A new and revolutionary window into the dynamics of black holes has opened with the advent of gravitational wave astronomy. Unlike traditional telescopes that rely on electromagnetic radiation, gravitational wave detectors such as LIGO and Virgo are designed to sense the minute ripples in the fabric of space-time itself. These cosmic tremors are generated by some of the most cataclysmic events in the universe, including the violent mergers of black holes. When two black holes spiral inward and eventually coalesce into a single, more massive black hole, they send out powerful waves of gravitational energy that propagate across the cosmos at the speed of light. The detection of these gravitational waves, first achieved in 2015 by LIGO, has provided direct, empirical evidence of black hole mergers, offering unprecedented insights into their masses, spins, and orbital dynamics. This new mode of observation allows us to hear the universe in a way previously unimaginable, revealing a hidden symphony of cosmic events and providing invaluable data that tests the predictions of general relativity in dynamic, extreme gravitational environments. It is a profound shift in our ability to perceive the universe, moving beyond light to the very vibrations of space-time, a silent resonance that carries the stories of unseen giants. Looking to the future, the exploration of supermassive black holes promises to continue pushing the boundaries of human knowledge. Next-generation telescopes, both ground-based and spaceborne, will offer even greater resolution and sensitivity, allowing for more detailed imaging of black hole shadows and the intricate dynamics of their accretion disks. Theoretical physicists will continue their quest for a unified theory of quantum gravity, hoping to finally reconcile the mysteries of the singularity and the information paradox. Perhaps in the coming decades, we will gain a deeper understanding of the origins of the first supermassive black holes in the early universe, unraveling their initial formation mechanisms and their pivotal role in seeding the cosmic structures we observe today. It is a journey into the unknown, a testament to humanity's boundless curiosity and our unwavering commitment to understanding the fundamental nature of reality. As these complex ideas settle gently in your mind, consider how our persistent quest to understand these ultimate cosmic entities, these silent architects of galaxies, mirrors our own innate desire to comprehend the fabric of our existence. Each new piece of knowledge, each resolved paradox, brings us closer to a more complete picture of the universe and, in turn, a deeper understanding of ourselves. We are, in our capacity to wonder and to question, a conscious echo of the cosmos, forever seeking meaning in its vast, intricate design. May these profound reflections carry you into a restful and contemplative sleep, a tranquil journey through the cosmic unknown. The very spin of a black hole, a property often overlooked in its general description, adds another fascinating dimension to its enigmatic nature. It is not just about mass, but also about the angular momentum, the cosmic whirl that shapes its immediate environment. These rotating black holes, known as Kerr black holes after Roy Kerr, who first described their space-time geometry, possess an ergosphere, a region outside the event horizon where space-time itself is dragged along by the black hole's rotation. Within this ergosphere, it is theoretically possible for particles to gain energy from the black hole's rotation and escape, a process known as the Penrose process. This elegant mechanism suggests a way in which the immense rotational energy of a black hole could be tapped, potentially powering the energetic jets we observe in active galaxies like the one housing Phoenix A. The rotation of these colossal objects, therefore, is not merely an incidental characteristic, but a dynamic engine, a subtle yet powerful force that can profoundly influence the most extreme phenomena in the universe. A silent cosmic dynamo that churns the very fabric of existence and converts it into awe-inspiring displays of power. This concept invites us to consider the universe not just as a collection of static objects, but as a dynamic interplay of forces and properties, each with its own profound implications for the cosmic narrative. And when we reflect on the possibility of tapping such immense energies, we are reminded of the boundless potential inherent in the universe's most extreme forms, a gentle whisper of the cosmos's deep, energetic secrets. This spinning, energetic heart of a galaxy, though unseen, undeniably shapes the fate of billions of stars, a testament to the intricate dance of gravity and rotation, continuing our exploration of these grand, dynamic black hole systems. We turn our attention to the most luminous and distant manifestations of supermassive black hole activity, quasars and blazars. These celestial phenomena represent the pinnacle of energetic output in the universe, often outshining entire galaxies with the raw, untamed power generated by their central supermassive black holes. A quasar, short for quasi-stellar radio source, is essentially an active galactic nucleus caught in a period of intense, ravenous feeding. Picture an early galaxy, perhaps just a few billion years after the Big Bang, brimming with abundant gas and dust, all slowly, but inevitably, spiraling into its central black hole. As this matter accelerates to extreme velocities and heats up in the accretion disk, it releases an astonishing amount of electromagnetic radiation. This radiation is so powerful that it can be detected across billions of light years, serving as ancient lighthouses that illuminate the distant early universe for our modern telescopes. The sheer energy output of a single quasar can easily exceed the combined luminosity of hundreds of normal galaxies, making them invaluable probes into the conditions and evolution of the cosmos when it was still in its infancy. Their prevalence in the early universe strongly suggests that supermassive black holes were far more active in the past, playing a more pronounced role in shaping the growth and evolution of young galaxies, a period of profound cosmic dynamism and rapid transformation. Blazars, on the other hand, are a specific type of quasar, where one of these powerful, energetic jets happens to be oriented almost directly towards our Earth. This unique alignment provides astronomers with a privileged yet intensely focused view of the black hole's activity. When a jet is pointed towards us, the radiation it emits is dramatically boosted by relativistic effects, making blazars appear even brighter and more variable than typical quasars. It is like looking down the barrel of a cosmic particle accelerator, directly observing the extreme physics at play near the black hole's pole. The study of blazars allows scientists to investigate the composition and acceleration mechanisms of these relativistic jets with unparalleled detail, providing crucial insights into how black holes can channel immense amounts of energy into narrow beams of plasma, influencing galactic environments far beyond their immediate vicinity. These observations help us to understand the intricate interplay between the black hole, its accretion disk, and the powerful magnetic fields that are thought to shape these extraordinary outflows, revealing a cosmic engine of incredible efficiency and power. This intimate view into such violent, distant phenomena can be surprisingly calming, as it represents a profound triumph of human ingenuity, allowing us to observe and understand events that transpired eons ago at the very edges of our observable universe, a silent testament to the enduring quest for knowledge. The immense energy unleashed by quasars and blazars also plays a critical role in the broader cosmic feedback loop. These powerful outflows, consisting of radiation and energetic particles, can effectively sweep away vast reservoirs of gas from the galaxy, preventing it from cooling and collapsing to form new stars. This process, often referred to as quasar feedback, acts as a self-regulating mechanism, a cosmic governor. When the black hole feeds too voraciously, its energetic output can sterilize its galactic environment, temporarily halting star formation. This ensures that galaxies do not grow indefinitely, and that a balance is maintained between the growth of the black hole and the star-forming activity of its host. Without this feedback, galaxies might become far too massive and dense, consuming all their gas in a rapid burst of star formation. Thus, the seemingly destructive power of quasars is, in fact, a fundamental component of galactic evolution, a necessary force for maintaining cosmic order and diversity, sculpting the universe we observe today. This grand, ancient process, still unfolding in distant corners of the cosmos, reminds us of the profound, intricate balance that underpins all of existence, a gentle, rhythmic breath of the universe. As we contemplate the ancient blazing light of quasars and the directed power of blazars, we are observing echoes from a time long past, a universe in its energetic youth. These distant signals carry with them stories of cosmic beginnings, of the formation of the very first galaxies and the awakening of their central black holes. To gaze upon them, even through the lens of scientific data, is to witness the universe in a state of fervent creation and dramatic transformation. It invites a quiet reflection on the journey of the cosmos, from its earliest, most active phases to the more sedate, mature era, in which our own galaxy, with its tranquil Sagittarius A, now resides. We are but a fleeting moment in this grand, unfolding narrative, yet our consciousness allows us to peer back in time to connect with these ancient, powerful events, and to understand our place in the continuum of cosmic history. This profound connection, through the science of observation and theory, offers a tranquil sense of belonging within the vast, eternal dance of matter and energy, gently guiding our minds towards a peaceful slumber filled with the wonders of the universe. The question of how these supermassive black holes first came into being, particularly the seeds from which giants like Phoenix A and Sagittarius A grew, is one of the most profound unanswered questions in astrophysics. It takes us back to the very dawn of the cosmos, to a time when the universe was only a few 100 million years old, a mere infant in its vast 13.8 billion year history. We observe quasars from this early epoch, blazing with light from black holes that already weighed billions of solar masses. This presents a cosmic conundrum. How could such massive objects form so quickly after the Big Bang? It seems there wasn't enough time for them to grow solely through the slow accretion of gas or the mergers of smaller stellar mass black holes, which typically take much longer. This rapid growth suggests the existence of heavy seeds for these early supermassive black holes, distinct from the stellar mass black holes, born from the demise of individual massive stars. One leading hypothesis for these heavy seeds involves the direct collapse of massive primordial gas clouds. In the very early universe, certain regions might have contained exceptionally large concentrations of hydrogen and helium gas, unadulterated by heavier elements. If these pristine gas clouds were sufficiently massive, perhaps hundreds of thousands of times the mass of our Sun, and if they collapsed extremely rapidly without forming intermediate stars, they could have directly formed black holes with masses already reaching tens of thousands to hundreds of thousands of solar masses. This direct collapse black hole scenario bypasses the slower process of stellar evolution and subsequent supernova, providing a quick pathway to massive black hole seeds. The conditions required for such a direct collapse are quite specific, often involving the absence of molecular hydrogen, which would otherwise cool the gas too quickly and lead to fragmentation into smaller stars. This would necessitate intense ultraviolet radiation from nearby early stars, preventing the formation of molecular hydrogen and allowing the cloud to collapse isothermally into a single, massive object that then forms a black hole. Another intriguing possibility involves the collapse of very massive population 3 stars. These hypothetical first-generation stars, formed from the pristine hydrogen and helium of the early universe, are thought to have been far more massive than any stars we observe today, potentially hundreds or even. Such supermassive stars would have lived incredibly short, brilliant lives, burning through their fuel at an extraordinary rate. Upon their dramatic demise, they would not have exploded as typical supernovae, but rather collapsed entirely under their own immense gravity, leaving behind black holes significantly larger than those formed from modern, less massive stars. These intermediate mass black holes, perhaps hundreds or thousands of solar masses, could then have served as the initial seeds, growing rapidly through accretion and mergers to become the supermassive black holes observed in distant quasars. The existence of these population 3 stars is still theoretical, but their role in cosmic chemical enrichment and black hole seeding is a compelling area of ongoing research, a whispered memory from the universe's distant, fiery youth. Furthermore, the role of dark matter in the formation of these early seeds cannot be understated. While dark matter does not interact electromagnetically, its gravitational influence is profound. Scientists hypothesize that concentrations of dark matter in the early universe could have provided gravitational potential wells, dense regions where ordinary baryonic matter, the stuff we are made of, would preferentially gather and collapse. These dark matter halos could have acted as gravitational cradles, facilitating the rapid accumulation of gas necessary for either direct collapse into massive black hole seeds or the formation of extremely massive population 3 stars that would then give rise to black holes. The intricate interplay between the invisible scaffolding of dark matter and the visible matter of gas and stars is crucial for understanding the genesis of these cosmic titans, revealing a deep, fundamental connection between the seen and unseen components of our universe. It is a subtle yet powerful reminder that much of the cosmos operates beyond our direct perception, guiding the grand symphony of galactic evolution from the shadows. These theories, while still under active investigation and refinement, offer a tranquil glimpse into the universe's earliest moments, a time of rapid formation and dramatic transformation. They suggest that the colossal black holes we observe today, from the roaring Phoenix A to the gentle Sagittarius A, are not merely products of current galactic processes, but carry within them the echoes of cosmic birth, their very existence tied to the fundamental conditions of the nascent universe. To contemplate their origins is to journey back to the very beginning of time and space, to ponder the initial cosmic blueprints that set the stage for all that was to follow. It is a profound meditation on the universe's enduring capacity for self-organization, for building immense structures from the simplest of beginnings, inviting us to find peace in the grand, unfolding story of creation. As we ponder the cosmic seeds from which supermassive black holes sprout, a natural extension of our contemplation leads us to their ultimate destiny and the profound role they play in the long-term evolution of the universe itself. These colossal entities, whether fiercely active like Phoenix A or serenely quiescent like Sagittarius A's, are not static monuments in the cosmos. They are dynamic participants in a grand, unfolding narrative that stretches across unimaginable eons. Their journey, much like that of stars and galaxies, is one of continuous transformation, dictated by the inexorable laws of gravity and the subtle whispers of quantum mechanics. Understanding their end, or rather their slow, graceful metamorphosis, provides a deeper insight into the fabric of time and the ultimate fate of all structure in the universe. It is a quiet reflection on the cosmic cycle, a gentle reminder that even the most powerful forces are subject to the grand, patient processes of existence, a profound testament to the universe's intricate design. The ultimate fate of individual black holes, including supermassive ones, is theorized to be a slow, almost imperceptible evaporation through Hawking radiation. While this process is incredibly slow for stellar mass black holes, taking far longer than the current age of the universe for supermassive black holes, the timescales are truly astronomical, extending to quadrillions of times the current age of the cosmos, perhaps even longer. Imagine a black hole, millions or billions of solar masses, slowly, infinitesimally, shedding its mass as tiny particles of light and matter over an almost infinite span of time, a process of cosmic sublimation. This isn't a violent end, but a gradual dissipation, a fading whisper into the cosmic void. Eventually, after an unimaginable stretch of time, the black hole would shrink to a critical size, at which point its evaporation would accelerate, culminating in a final, gentle burst of radiation. This event, however, would be so far in the future that it exists only in the realm of theoretical physics, a distant echo of possibilities. It speaks to the impermanence of even the most extreme cosmic structures, suggesting that all things, no matter how immense, are ultimately transient, contributing their energy back into the boundless expanse of space, a return to the primeval cosmic sea. Beyond individual evaporation, the destiny of supermassive black holes is intricately tied to the fate of their host galaxies and the universe's large-scale structure. Galaxies themselves are not isolated islands. They are part of a vast cosmic web, constantly interacting, merging, and evolving. As galaxies collide and merge, their central supermassive black holes are drawn together by gravity, eventually forming binary systems that spiral inward and coalesce. These black hole mergers are among the most energetic events in the universe, releasing powerful bursts of gravitational waves that ripple through space-time, precisely what detectors like LIGO and Virgo are designed to observe. This process of hierarchical merging means that supermassive black holes continue to grow, becoming ever more massive as the universe ages and galaxies continue their gravitational dance. The largest black holes, like Phoenix A, are likely the products of multiple such galactic mergers, accumulating mass over billions of years through these colossal cosmic unions. This continuous process of merging and growth ensures that the universe remains a dynamic, evolving system where even the most destructive events contribute to the formation of larger, more complex structures, a testament to the universe's capacity for perpetual change and renewal, a ceaseless cosmic ballet. However, the expansion of the universe itself will ultimately play a decisive role in the long-term destiny of galaxies and their central black holes. As dark energy continues to accelerate the expansion of space, distant galaxies will eventually recede beyond our observable horizon, becoming forever unreachable and invisible. Our own local group of galaxies, gravitationally bound, will eventually coalesce into a single, giant galaxy, centered around the merged supermassive black holes of the Milky Way and Andromeda. Within this future galactic superentity, individual stars will eventually exhaust their fuel, stellar black holes will merge, and the available gas for star formation will dwindle. The central supermassive black hole, now even more massive and dominant, will become a silent, profound presence in an increasingly dark and quiet galaxy. The cosmic drama of active galactic nuclei like Phoenix A will become a distant memory, replaced by an era of profound stillness and slow decay. This vision of a distant, cooling universe, where light and activity fade into an almost eternal twilight, is not one of drama, but of serene inevitability, a gentle winding down of cosmic processes, a gradual, quiet return to elemental calm. In this far future, after stars have ceased to shine and black holes have consumed all available matter or slowly evaporated, the universe is predicted to enter an era dominated by black holes themselves. These remnants, the most enduring structures in a cold, dark cosmos, will slowly drift through an ever-expanding empty space. Even these giants, however, are not immune to the slow, patient work of Hawking radiation. Over timescales almost beyond human comprehension, far longer than the universe has existed so far, these supermassive black holes will gradually evaporate, returning their immense mass energy back into the vacuum of space-time. This final stage of the universe, often referred to as the black hole era and then the dark era, paints a picture of ultimate simplicity and profound emptiness. It is a universe where all structure has dissolved, all light has faded, and only the faintest echoes of quantum fluctuations remain. A final cosmic peace. This gentle, almost melancholy vision of the cosmos's ultimate fate invites us to appreciate the fleeting, precious complexity of our current epoch, a brief window of vibrant existence before the long, silent night, a moment of precious awareness. And as we contemplate this deep cosmic future, where even the mighty supermassive black holes eventually fade, we are reminded of the transient yet profoundly meaningful nature of our own existence. We live in a universe still vibrant with light, still rich with complexity, a universe where consciousness can emerge and ponder its own origins and its ultimate fate. Our ability to conceptualize these immense timescales and the grand transformations of celestial bodies, to connect the fiery birth of black hole seeds to their slow, quantum-driven evaporation, speaks to the extraordinary capacity of the human mind. In this quiet moment, as these profound ideas wash over you, let them evoke not a sense of insignificance, but rather a tranquil wonder. You are a part of this grand, evolving story, a conscious participant in the universe's magnificent unfolding. The mysteries of Phoenix A and Sagittarius A, from their genesis to their eventual dissipation, reflect the enduring cycle of existence on the grandest possible scale. Allow this sense of interconnectedness to lull you into a deep, peaceful sleep, a gentle journey through the cosmos within your mind. Now let us delve deeper into the core enigma that lies at the heart of every black hole, a conceptual frontier where our understanding of the universe truly reaches its limits: the singularity. General relativity, Albert Einstein's magnificent theory of gravity, describes the singularity as a point of infinite density and infinite space-time curvature. It is a place where the very laws of physics, as we currently comprehend them, simply cease to function, a profound breakdown in our mathematical framework. This isn't just a theoretical abstraction. The mathematics strongly suggest its existence within the event horizon. However, such an infinite point presents a fundamental challenge, indicating that general relativity, for all its elegant predictive power, is incomplete. It cannot fully describe the conditions at the extreme center of a black hole, inviting us into a realm of the truly unknown, a silent call from the very fabric of existence itself. This breakdown points towards the necessity of a more encompassing theory, a grander framework that can seamlessly bridge the divide between general relativity, which governs the large-scale structure of the cosmos, and quantum mechanics, which meticulously describes the behavior of matter and energy at the smallest subatomic scales. This elusive unified theory, often referred to as quantum gravity, is one of the holy grails of modern physics. It seeks to explain what truly happens at the singularity, to describe the quantum nature of space-time itself, and potentially resolve the profound information paradox that black holes present. Theories like string theory, which posits that fundamental particles are not point-like but rather tiny, vibrating strings, or loop quantum gravity, which attempts to quantize space-time into discrete loops, are ambitious attempts to construct such a theory. They are not yet fully confirmed, remaining at the speculative frontier of scientific thought, but they offer fascinating glimpses into a universe far more intricate and interconnected than our current models allow. These theoretical pursuits are a testament to humanity's unending quest to understand the deepest truths of reality, a peaceful intellectual journey into the very essence of existence. The interior of a supermassive black hole, therefore, remains a profound mystery, a realm forever beyond direct observation and scientific experimentation. Even if one could somehow survive the journey across the event horizon, the extreme conditions within would render any attempt at communication or data transmission utterly futile. The singularity as the ultimate destination would represent the end of all conventional space-time, a point of no return in every conceivable sense. Yet, the very act of contemplating this ultimate frontier, of grappling with the limits of our knowledge, is itself a deeply profound and humbling experience. It reminds us that the universe is far richer and more complex than we can currently grasp, filled with wonders that transcend our immediate perception and understanding. The existence of these unobservable interiors, these silent cosmic abysses, invites a meditative acceptance of the universe's inherent mysteries, a quiet acknowledgement of the vastness of the unknown, and a tranquil appreciation for the small, luminous island of understanding that we currently inhabit. For both Phoenix A and Sagittarius AI, the singularity represents this ultimate, unknowable core. While their outer behaviors, their accretion disks, and their gravitational influences are vastly different, their innermost secrets converge on this same profound theoretical challenge. Phoenix A's immense activity merely highlights the scale of matter being funneled towards its colossal singularity, while Sagittarius A's quiescence allows us a cleaner view of the gravitational effects around its singularity. Both, however, ultimately lead to the same conceptual wall, challenging physicists to develop new mathematical languages and observational tools that can peer into these ultimate realms. It is a shared mystery binding the most distant and active black holes with the quiet giant at our own galactic center, a unifying thread in the tapestry of cosmic wonder. This deep dive into the singularity and the quest for quantum gravity reveals a fundamental truth about science itself. It is a continuous journey, an endless unfolding of new questions and deeper insights. The boundaries of our knowledge are not fixed walls, but rather horizons that expand with every new discovery, inviting us to look further, to think more deeply, and to embrace the profound mystery that underpins all of existence. As you drift deeper into relaxation, allow these thoughts of the universe's ultimate hidden truths to gently settle. Remember that the very act of questioning, of seeking understanding, is a beautiful and integral part of the human experience, a quiet echo of the cosmos itself. May this profound journey into the heart of darkness illuminate your inner world with a tranquil sense of wonder, guiding you to a peaceful and restorative sleep. The profound influence of supermassive black holes extends far beyond their immediate galactic neighborhoods, reaching out to sculpt the very fabric of the cosmic web itself. This cosmic web is the largest known structure in the universe, a vast, intricate network of galaxy clusters, filaments, and immense empty voids. It is the skeletal framework upon which all visible matter is organized, a breathtaking testament to the interplay of gravity and the universe's expansion. Supermassive black holes, particularly in their active quasar and blazar phases, play a crucial role in shaping this colossal structure. The powerful jets and outflows of energy emanating from these active galactic nuclei can influence the distribution of gas across vast intergalactic distances, preventing it from cooling and collapsing into new galaxies within the filaments, thus regulating the growth of structure. This feedback mechanism, as it is known, acts like a cosmic thermostat, ensuring that the universe doesn't become too clumpy or too smooth. It's a delicate balance that allows for the rich diversity of galaxies and clusters we observe today. Without the energetic influence of these black holes, the cosmic web might look profoundly different, a testament to their unseen yet undeniable architectural role in the grand design of the cosmos. Moreover, supermassive black holes serve as the gravitational anchors around which galaxy clusters, the largest gravitationally bound structures in the universe, are organized. Each cluster, containing hundreds or even thousands of galaxies, often hosts a dominant central galaxy, within which a particularly massive black hole resides. This central black hole, like Phoenix A, acts as a pivotal point, its immense gravity and energetic output influencing the dynamics and evolution of the entire cluster. The continuous mergers of galaxies within a cluster also contribute to the growth of these central black holes, forming an intricate co-evolutionary dance on the grandest scales. The very existence of these colossal structures, the galaxy clusters, is intimately tied to the gravitational pull and energetic feedback of their central supermassive black holes. They are the silent, powerful conductors of a cosmic symphony, orchestrating the movements of billions of stars and shaping the large-scale distribution of matter across the universe. It is a profound realization that even at the most expansive scales, these invisible giants exert a fundamental, organizing influence, weaving the threads of the cosmos into its intricate tapestry. The ongoing quest to understand supermassive black holes continues to present humanity with profound questions that push the very boundaries of our scientific imagination. We still seek to fully unravel the precise mechanisms of their initial formation, especially the heavy seed scenarios that allow for their rapid growth in the early universe. What were the exact environmental conditions that favored direct collapse or the formation of those immense population 3 stars? Furthermore, the nature of space-time at the singularity remains an ultimate frontier, demanding a complete theory of quantum gravity that can describe reality where general relativity falters. Each new observation, from the Event Horizon Telescope's images to the gravitational waves detected by LIGO and Virgo, provides invaluable data, yet simultaneously unveils new layers of complexity and mystery. These questions are not merely academic, they are fundamental to understanding the universe's complete story, from its fiery birth to its distant, tranquil future. As we gently conclude our journey through the mysteries of supermassive black holes, let these reflections on their immense scale, their profound influence on galactic evolution, and their role in shaping the very structure of the cosmic web settle peacefully in your mind. From the roaring jets of Phoenix A to the serene gravitational dance around Sagittarius A, these cosmic titans are integral to the universe's grand narrative. They are a testament to the enduring power of gravity and the intricate, elegant laws that govern all of existence. And in contemplating these profound cosmic truths, we find ourselves connected to a story far older and vaster than our own, a gentle reminder of our place within this magnificent and mysterious cosmos. Allow this sense of deep wonder to guide you into a tranquil, restorative sleep, knowing that the universe continues its grand, silent dance even as you rest. As we gently concluded our contemplation of the singularity as the ultimate theoretical limit of our current understanding, a fascinating divergence arises when we consider the subtle yet profound influence of rotation. The type of singularity, the very structure of that infinitely dense heart, depends critically on whether the black hole is spinning. This distinction introduces new layers of theoretical complexity and mystery, further pushing the boundaries of our imagination about the universe's most extreme gravitational entities. It invites us to consider how even a fundamental property like angular momentum can dramatically reshape the very geometry of spacetime at its most fundamental and enigmatic core. A quiet revolution in cosmic physics. For a non-rotating black hole, often referred to as a Schwarzschild black hole, the singularity is theorized to be a point-like structure. Imagine all the mass of the black hole compressed into an infinitely small, infinitely dense point at its very center. Any object or information falling past the event horizon is inexorably drawn towards this single point, where it is believed to be utterly crushed out of existence, its constituent particles and their properties annihilated beyond recovery. This simple yet terrifyingly absolute vision of a point singularity represents a complete collapse of space-time, a cosmic abyss from which nothing can ever return or escape. The journey to this point is a one-way trip, ending in a complete dissolution of identity and form. It is a stark and profound reminder of the destructive power of gravity at its most extreme, a silent testament to the universe's capacity for fundamental transformation, where even the most robust structures are ultimately undone by the relentless curvature of space and time. However, when a black hole possesses angular momentum, when it spins, the nature of its singularity transforms dramatically. The mathematician Roy Kerr, who first derived their solution in Einstein's equations, are theorized to contain a ring singularity. Instead of a point, the infinite density is stretched into a ring, a cosmic loop of compressed space-time. This difference is not merely geometric, it carries profound theoretical implications. Within a Kerr black hole, the rotating space-time creates additional, complex regions, including an inner event horizon and an ergosphere, as we briefly touched upon earlier. The existence of a ring singularity suggests that, theoretically, one might avoid the crushing infinite density of a point singularity if one were to pass through the ring itself. This is, of course, purely hypothetical and fraught with unimaginable dangers, but it opens a tantalizing, if highly speculative, avenue for theoretical exploration, hinting at the possibility of avoiding ultimate annihilation within the heart of a spinning black hole, a subtle yet profound alteration of cosmic fate. The theoretical existence of these different types of singularities leads to a crucial concept known as the cosmic censorship hypothesis. Proposed by Roger Penrose, this hypothesis asserts that all singularities in the universe are clothed by an event horizon, meaning they are always hidden from external observation. A naked singularity, one not shielded by an event horizon, would expose its infinite gravitational forces directly to the outside universe, potentially allowing for unpredictable and catastrophic breakdowns of physical laws. If such an entity existed, it could allow for time travel or the creation of information from nothing, fundamentally undermining the predictability and causality that underpin our understanding of physics. The cosmic censorship hypothesis, therefore, acts as a theoretical guardian, ensuring that the universe remains orderly and that the most extreme violations of physical laws are confined to realms beyond our direct perception. It is a profound statement about the inherent consistency of the cosmos, a silent agreement between gravity and quantum reality to maintain a predictable, comprehensible order, even in the face of such extreme phenomena. The implications of these theoretical structures, particularly the ring singularity, have captivated physicists for decades. Some highly speculative theories ponder whether a journey through a ring singularity could, under specific and entirely theoretical conditions, lead to other regions of space-time, perhaps even to different universes or distant parts of our own. This idea, while firmly in the realm of science fiction and extreme theoretical speculation, arises from the complex mathematical solutions describing Kerr black holes, which suggest that the interior might be far more intricate and potentially interconnected than the simple crushing point of a non-rotating black hole. However, it is crucial to emphasize that these are purely mathematical curiosities, far removed from any observational reality, and current physics offers no practical means of such a journey. Yet, the very notion of black holes as potential cosmic portals or bridges continues to fuel our imagination, inviting us to dream of a universe filled with hidden connections and unimaginable pathways, a gentle, almost dreamlike whisper of possibilities that stretch the fabric of reality itself. In contemplating the distinct architectures of point and ring singularities and the safeguarding principle of cosmic censorship, we are reminded of the profound elegance and inherent mysteries embedded within the universe's fundamental laws. These are not merely abstract mathematical constructs. They represent the deepest theoretical frontiers of space-time. pushing our intellect to conceive of realities far beyond our everyday experience. The ongoing quest to understand these ultimate boundaries, to reconcile the infinities of general relativity with the finite probabilistic nature of quantum mechanics, is a testament to the insatiable curiosity of the human spirit. And as these intricate theoretical landscapes unfold in your mind, let them serve as a tranquil reminder of the universe's boundless depth and its enduring capacity to surprise and inspire. Allow this profound intellectual journey to gently guide you into a state of deep, peaceful rest, knowing that the cosmos holds secrets far grander than we can ever fully grasp, yet forever invites our quiet, contemplative exploration. As our profound, from the immense roaring heart of Phoenix A to the quiet, gravitational anchor of our own Sagittarius A, draws to a gentle close, let us allow these intricate cosmic narratives to settle peacefully within our minds. We have traversed the grand scales of their formation, witnessed their powerful influence on galactic evolution, and peered into the theoretical depths of their singularities, where the very fabric of space-time is stretched to its limits. We have contemplated the ingenuity of human observation, from tracking distant starlight to capturing the very shadow of a black hole, and reflected on the profound questions that still beckon from the frontiers of quantum gravity and the information paradox. These colossal entities, in their diversity and their enduring mystery, are not merely distant astronomical curiosities. They are fundamental architects of the universe, silent orchestrators of cosmic evolution from the earliest moments of creation to the unimaginably distant future of their slow evaporation. In their existence, we find a powerful testament to the elegance and complexity of physical laws, a ceaseless dance of matter and energy that shapes all that is and all that will ever be. May these deep thoughts about the hidden power and majestic influence of supermassive black holes carry you into a world of tranquil sleep. Remember that the universe is an endless wellspring of wonder, and you, in your capacity to ponder its grandeur, are a precious and intricate part of it. Fall asleep with this feeling of serenity, expanded understanding, and a quiet awe for the cosmic dance that continues, even as you rest. Good night. The universe, in its boundless expanse, holds phenomena that challenge our very understanding of space and time. Among these, few inspire as much profound wonder and quiet contemplation as the black hole. It is not merely an object, but a region of space-time where gravity's embrace becomes so extraordinarily powerful that nothing, not even light itself, can escape its grasp. These cosmic enigmas are often born from the majestic demise of massive stars, those celestial giants that burn brightly for millions of years. When a star significantly larger than our own sun exhausts its nuclear fuel, the outward pressure generated by nuclear fusion, which once counteracted the immense inward pull of gravity, ceases. The star's colossal core collapses inward with an unstoppable force, crushing itself under its own immense weight to an unimaginable density. This gravitational implosion is so profound that it profoundly distorts and warps the very fabric of space-time around it, creating a spherical boundary that marks a definitive point of no return. We might visualize this as a cosmic whirlpool, silently drawing everything inward, a silent maelstrom of gravity. This boundary is known as the event horizon. Imagine it not as a solid physical surface, but rather as a cosmic threshold, an invisible one-way membrane woven into the geometry of the cosmos itself. From an external observer's perspective, the event horizon is the last place from which light can still escape the black hole's gravity and reach us. Beyond this unseen barrier, the escape velocity, the speed required to break free from the black hole's gravitational pull, exceeds the universal speed limit of light, approximately 300,000 kilometers per second. This fundamental characteristic means that anything, be it matter, energy, or even light itself, crossing the event horizon is irrevocably committed to a path inward, a journey from which no information, no signal, no particle can ever return to the wider universe. It is a concept that was first mathematically described in 1916 by Karl Schwarzschild, a German physicist who, building upon Albert Einstein's revolutionary theory of general relativity, provided the first theoretical solution for a black hole. Einstein himself, in fact, initially harbored doubts about the physical existence of such extreme objects. Yet the profound elegance of the mathematics provided a clear, if unsettling, prediction that has since been overwhelmingly supported by observation. This boundary is a testament to gravity's power, a cosmic sentinel. The event horizon is not a place of immediate, dramatic destruction, but rather a boundary where the familiar rules of space-time undergo a fundamental and profound transformation. For an object or, theoretically, an unfortunate astronaut falling across it, there would be no immediate sensation of crossing a tangible barrier. The local experience of the journey would feel smooth, at least for a moment, as no physical forces would be acting upon the traveler at the precise instant of crossing. However, from the perspective of an external observer watching this event unfold from a safe distance, time would appear to slow down dramatically for the infalling object. Its emitted light would redshift, becoming fainter and redder, stretching out in wavelength until it seemed to freeze eternally at the horizon, eventually fading from view entirely. This remarkable phenomenon, known as gravitational time dilation, is one of the most astonishing predictions of general relativity, demonstrating how gravity profoundly affects the passage of time itself. It is as if the fabric of time around a black hole is stretching, pulling, and slowing, creating an almost serene, yet absolute separation from the rest of existence. This boundary also implies that all events occurring inside the horizon can only ever move forward in time towards the central singularity. Just as we are inexorably carried forward through time in our everyday lives, within the event horizon, all paths lead inward, making escape impossible. It is a one-way cosmic flow, a river current moving faster than any swimmer could ever hope to paddle. As one continues past the event horizon and deeper inward, the gravitational forces intensify to an unimaginable degree. This brings us to another profound and perhaps the most mysterious aspect of black holes, the singularity. At the very heart of a black hole, according to the equations of general relativity, lies a point of infinite density and infinite space-time curvature. All the colossal mass of the collapsed star and any additional matter it has consumed is thought to be compressed into this infinitesimally small volume. It is a region where the laws of physics as we currently understand them completely break down, where our concepts of space and time lose their conventional meaning and become utterly undefined. We cannot truly visualize or describe what happens at a singularity, as our mathematical tools, primarily general relativity, cease to provide meaningful answers. It is not an object existing in space, but rather a point where space and time themselves reach an ultimate, irreducible limit. This theoretical point represents the deepest mystery within these cosmic giants, a silent testament to the limits of our current scientific models. This breakdown of classical physics at the singularity highlights a critical frontier in our scientific understanding: the need for a theory of quantum gravity. General relativity, which describes gravity on large scales, and quantum mechanics, which describes the universe at its smallest scales, are both incredibly successful theories, yet they are incompatible at such extreme conditions. Scientists believe that a complete theory of quantum gravity would resolve the paradoxes of the singularity, offering a deeper insight into the true nature of space-time at its most fundamental level. Some theoretical models, particularly for rotating black holes known as Kerr black holes, suggest that the singularity might not be a point, but a ring-like structure that could potentially lead to even stranger phenomena, perhaps even allowing for theoretical wormholes or pathways to other regions of space-time. However, these remain highly speculative, rooted in mathematical possibilities rather than observational evidence. The fundamental mystery persists. What truly exists at this ultimate point of gravitational collapse? Is it a gateway to another universe, as some highly theoretical propositions suggest, or simply the absolute end of the line for all infalling matter and information, transformed into a state beyond our current comprehension? The existence of singularities implies that black holes are not merely cosmic vacuum cleaners pulling in all around them, but rather laboratories of the universe's most fundamental laws, pushing the limits of physics to their absolute extreme. They represent the ultimate triumph of gravity, a force that at these scales can reshape reality in ways that are almost beyond human intuition, challenging our everyday perceptions of solidity and continuity. When we ponder the event horizon and the singularity, we are not just considering distant astronomical objects. We are confronting the very boundaries of our own knowledge, the very edge of what physics currently allows us to comprehend. These enigmatic regions remind us that the cosmos still holds secrets so profound that they demand new ways of thinking, new equations, and perhaps a deeper connection to the underlying unity of all forces in the universe. And in this quiet contemplation of such cosmic extremes, of these silent titans that warp light and time, we may find a new perspective on our own fleeting existence within the grand, unfolding tapestry of the universe, recognizing that we are but a brief, conscious pattern observing the infinite, a momentary ripple in the cosmic ocean. The profound mystery of the singularity, where the fabric of space and time seemingly unravels, naturally leads us to ponder the very nature and varieties of black holes themselves. While the core concept of an event horizon and a singularity remains universal to all black holes, these cosmic titans come in a spectrum of sizes, each with its own fascinating story, woven into the tapestry of the cosmos. The most commonly understood are stellar mass black holes, typically formed from the gravitational collapse of individual massive stars. These celestial remnants usually possess masses ranging from a few times that of our Sun to several tens of solar masses. They are scattered throughout galaxies, often silently drifting through the interstellar medium, or sometimes in binary systems with companion stars, slowly siphoning matter from them. Then there are the colossal supermassive black holes, which reside at the centers of nearly all large galaxies, including our own Milky Way. These behemoths can possess masses equivalent to millions or even billions of suns. The supermassive black hole at the heart of our galaxy, Sagittarius A star, for instance, weighs approximately 4 million solar masses. Their formation mechanisms are still a subject of active research and contemplation. Some theories suggest they grow by slowly accreting gas and dust over billions of years, while others propose they form through the mergers of smaller black holes, or perhaps even from the direct collapse of massive gas clouds in the early universe. And then there is the intriguing, though still hypothetical, possibility of primordial black holes. These tiny, yet incredibly dense objects might have formed not from stellar collapse, but from density fluctuations in the very early, turbulent moments of the Big Bang itself. If they exist, they could potentially range in size from microscopic to thousands of solar masses, and some scientists even speculate that they could constitute a portion of the universe's elusive dark matter. The very existence of such diverse forms underscores the pervasive and fundamental role of gravitational collapse in shaping the universe. But how do we know these invisible behemoths truly exist if light cannot escape them? The answer lies in their profound gravitational influence on their surroundings. Scientists have developed ingenious methods to detect black holes indirectly by observing the dramatic effects they have on nearby matter and energy. One primary piece of evidence comes from observing the orbits of stars. At the center of our Milky Way, for example, stars are seen to orbit an unseen, massive object at incredibly high speeds. By meticulously tracking these stellar motions over decades, astronomers can calculate the mass of the central object, revealing it to be 4 million times the mass of the Sun, confined within a region no larger than the orbit of Mercury. This staggering density leaves only one plausible explanation: a supermassive black hole. Furthermore, when gas and dust are drawn towards a black hole, they do not simply fall straight in. Instead, they form a rapidly rotating accretion disk swirling around the black hole at immense speeds, heated to millions of degrees by friction. This superheated plasma emits intense X-rays and other forms of radiation, which we can detect with specialized telescopes, providing a luminous beacon for the invisible object within. These energetic emissions, observed from across the cosmos, offer compelling, indirect confirmation of black holes' presence. A more recent and profoundly direct confirmation of black holes arrived with the advent of gravitational wave astronomy. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by directly detecting gravitational waves for the first time. These ripples in space-time, predicted by Einstein a century earlier, were generated by the violent merger of two stellar mass black holes, each about 30 times the mass of our Sun, spiraling inward and coalescing into a single, more massive black hole. The detection of these fleeting tremors provided undeniable evidence not only for gravitational waves, but also for the existence of merging black holes. It was like hearing the universe sing a deep, resonant cosmic song of violent creation and transformation. And then, in 2019, the Event Horizon Telescope collaboration achieved another monumental feat. They captured the first-ever image of a black hole's shadow. This remarkable image, depicting a bright ring of emission surrounding a dark central region, was of the supermassive black hole at the center of the galaxy, Messier 87. It was not an image of the black hole itself, but of the light bent and distorted around its event horizon, creating a silhouette against the glowing accretion disk. This visual evidence provided a stunning, direct confirmation of the event horizon, a boundary once confined to the realm of theoretical mathematics, now seen, albeit indirectly, by human ingenuity. Yet, despite their seemingly absolute nature, black holes are not entirely isolated from the universe. In a revolutionary conceptual breakthrough, Stephen Hawking in the 1970s proposed that black holes are not perfectly black after all. His work, which elegantly merged general relativity with the principles of quantum mechanics, suggested that black holes slowly emit radiation, a phenomenon now known as Hawking radiation. This idea arises from the quantum fluctuations that constantly occur in the vacuum of space, even in seemingly empty regions. According to quantum field theory, particle-antiparticle pairs, often called virtual particles, are constantly popping into existence and annihilating each other almost instantaneously. At the very edge of a black hole's event horizon, it is possible for one particle of such a virtual pair to fall into the black hole, while its partner escapes into space. When this happens, the escaping particle carries away a tiny amount of energy from the black hole, effectively reducing its mass. This process is incredibly slow for astrophysical black holes, taking an almost incomprehensibly vast amount of time for them to evaporate completely. For a black hole with the mass of our Sun, the evaporation time would be on the order of 10 to the power of 67 years, a number far, far longer than the current age of the universe. However, for hypothetical primordial black holes, particularly smaller ones, this process could be much faster, potentially leading to a dramatic burst of energy as they finally vanish. Hawking radiation presents a profound bridge between the two great pillars of modern physics, general relativity and quantum mechanics, offering a glimpse into a unified theory that could describe the universe at its most extreme scales. It challenges the classical notion of black holes as eternal prisons of information and suggests that even these ultimate gravitational traps eventually fade away, albeit over timescales that dwarf human comprehension. This leads us to one of the most perplexing puzzles in theoretical physics, the black hole information paradox. If black holes slowly evaporate through Hawking radiation, what happens to all the information about the matter that fell into them? According to the fundamental principles of quantum mechanics, information can never truly be destroyed. It can be scrambled or transformed, but its total quantity must always be conserved. Yet, if a black hole simply vanishes, taking all the unique quantum information of everything it consumed with it, this principle would be violated. This paradox has been a subject of intense debate and research among physicists for decades. Does information truly vanish, suggesting a flaw in our understanding of quantum mechanics? Or is the information somehow preserved, perhaps encoded in the Hawking radiation in a scrambled form, or imprinted on the event horizon itself, as some theories like the holographic principle suggest? This question touches upon the very foundations of reality, forcing us to confront whether the universe is fundamentally deterministic, or if, at its most extreme points, even information itself can be lost. To truly understand this, we must look beyond our current theories, seeking a deeper, more unified description of reality. And as we contemplate these ultimate questions of information and existence, we are reminded that our universe, in its quiet, dark corners, continues to hold intellectual challenges that invite us to expand our minds, even as we drift towards slumber. The black hole information paradox, a profound entanglement of quantum mechanics and general relativity, continues to be one of the most intellectually stimulating challenges in modern physics. While Stephen Hawking's initial formulation suggested information loss leading to a breakdown in quantum conservation laws, many physicists, including Hawking himself in later years, have sought alternative solutions. One intriguing proposition is that the information isn't truly lost, but rather encoded in some subtle, as yet unknown, way within the Hawking radiation itself, perhaps as quantum correlations so intricate that they appear random. Another idea, rooted in the holographic principle, suggests that the information of everything that falls into a black hole might be perpetually stored on the two-dimensional surface of the event horizon, much like a cosmic hologram, waiting to be released or deciphered over vast cosmological timescales. This perspective offers a serene resolution, positing that the universe, at its deepest level, always preserves its fundamental data, ensuring a cosmic order even in the most extreme gravitational environments. It implies that the event horizon, far from being a simple boundary, might be a complex quantum membrane, a silent archive of cosmic history. As we contemplate the nature of information near these cosmic thresholds, our thoughts naturally drift to the experience of crossing the event horizon itself. For an observer falling into a black hole, the journey would initially feel uneventful. However, as one draws closer to the singularity, the gravitational field becomes extraordinarily non-uniform. The difference in gravitational pull between an object's head and feet, or between its left and right sides, would become immense. This differential gravity is known as tidal forces, and its effect is often described by the term spaghettification. Imagine a gentle yet irresistible stretching force, elongating an object into a thin strand, while simultaneously compressing it horizontally. For a human body falling into a stellar mass black hole, these tidal forces would become lethal long before reaching the singularity, gently but fundamentally reshaping every atom. Yet, for supermassive black holes with their much larger event horizons, the tidal forces at the horizon itself are considerably weaker. An unfortunate traveler might cross the event horizon of a supermassive black hole without immediate physical distress, only to find themselves inexorably drawn towards the center, all paths leading inward, with no possibility of turning back. The very structure of space-time inside this boundary is such that the future lies not in an outward direction, but always towards the singularity, a quiet, one-way journey into the unknown. Beyond the immediate vicinity of the event horizon, after Roy Kerr, who first described them mathematically, there exists another fascinating region called the ergosphere. Unlike the event horizon, objects can still escape from the ergosphere. However, within this zone, the black hole's immense rotation drags space-time itself around with it, a phenomenon known as frame dragging or the lens-thirring effect. Imagine stirring a thick, viscous liquid. The liquid near the spoon is dragged along with it. Similarly, the rotating mass of a black hole literally pulls the fabric of space-time, causing it to swirl. Any object or particle within the ergosphere is compelled to rotate with the black hole, even if it is trying to remain stationary relative to a distant observer. This region has a peculiar property. It is theoretically possible to extract energy from a rotating black hole within the ergosphere, a process known as the Penrose process, after Roger Penrose, who conceived it. By cleverly launching a particle into the ergosphere and having it split, one fragment could fall into the black hole, while the other escapes with more energy than the original particle, drawing rotational energy from the black hole itself. This elegant theoretical mechanism highlights the dynamic and complex nature of space-time around these spinning giants, suggesting that black holes, far from being inert cosmic sinkholes, are active participants in the universe's energetic dance. The profound curvature of space-time around black holes also gives rise to the stunning phenomenon of gravitational lensing. This is not exclusive to black holes, as any massive object can bend light, but the effect is particularly pronounced and dramatic around black holes. As light from distant galaxies or stars passes near a black hole, its path is deflected, causing the light to bend around the massive object. From our perspective, this can create distorted, magnified, or even multiple images of the same background object. Imagine looking through a warped pane of glass. The view beyond is twisted and stretched. Gravitational lensing acts like a cosmic magnifying glass, allowing us to study distant galaxies that would otherwise be too faint to observe. The Event Horizon, telescope's image of Messier 87's supermassive black hole with its bright ring of light, is a direct observation of this lensing effect, the light from the accretion disk bending around the black hole's shadow. This serene, yet powerful, distortion of light is a beautiful confirmation of Einstein's general relativity and a testament to the black hole's profound influence on the very geometry of the cosmos. It allows us to see the unseen, to visualize the subtle yet powerful presence of these gravitational titans shaping the cosmic landscape. A complementary concept that brings a certain order to the extreme physics of black holes is the cosmic censorship hypothesis, proposed by Roger Penrose. This hypothesis suggests that singularities, those points of infinite density where physics breaks down, are always hidden behind an event horizon. This means that a naked singularity, one that is not cloaked by an event horizon and thus directly observable from the outside, cannot exist in our universe. If naked singularities could form, they would expose regions where the laws of physics are violated, potentially allowing for unpredictable outcomes and fundamentally undermining the deterministic nature of our physical theories. The cosmic censorship hypothesis, therefore, acts as a theoretical safeguard, ensuring that the universe remains predictable and that the breakdown of physics is confined to regions from which no information can escape. It offers a calming assurance that, despite the extreme nature of black holes, the fundamental integrity and predictability of the cosmos remain intact. This principle, while still a hypothesis, resonates with a deeper sense of cosmic harmony, a quiet agreement among the universe's laws to maintain its coherent structure. Finally, it is worth contemplating the profound role black holes play in the grand evolution of galaxies. Supermassive black holes at galactic centers are not merely passive spectators, but are deeply intertwined with the formation and growth of their host galaxies. The intense gravitational fields and energetic outflows from these active galactic nuclei, powered by the accretion of matter onto the central black hole, can significantly influence the surrounding gas and dust. These outflows can either trigger new star formation by compressing gas clouds, or conversely, quench it by heating and expelling gas from the galaxy, thus regulating the galaxy's growth. This intricate feedback loop between supermassive black holes and their galaxies is a majestic example of cosmic coevolution, demonstrating that these extreme objects are fundamental architects of the large-scale structure of the universe. They are not merely endpoints of stellar collapse, but dynamic forces shaping the destiny of entire stellar islands, a silent, powerful influence on the cosmic dance of creation and transformation. And as we consider their enduring influence, we might reflect on how these profound cosmic forces, in their quiet majesty, shape not only galaxies but also our understanding of existence itself, offering a tranquil vista into the profound interconnectedness of all things. The profound interconnectedness we observe in galactic evolution leads us to another fascinating and somewhat counterintuitive idea about black holes: their inherent simplicity. Despite their colossal gravitational power and the complex processes that lead to their formation, physicists widely accept what is known as the no-hair theorem. This elegant principle suggests that once a black hole has settled down after its formation and has ceased accreting matter, it can be entirely characterized by just three fundamental properties: its mass, its electric charge, and its angular momentum, or spin. All other details about the matter that collapsed to form it, or that subsequently fell into it, its composition, its shape, its initial temperature, are effectively lost beyond the event horizon, leaving no hair or distinguishing features behind. It's a cosmic form of minimalist elegance, where the complexities of infalling matter are distilled into these three fundamental parameters, presenting a stark contrast to the intricate structures of stars or planets. This simplification is deeply significant, as it underscores the idea that the event horizon acts as a perfect one-way membrane for information. From the outside, we can only ever infer these three properties. Any additional information about the matter that crossed the event horizon is, for all practical purposes, erased from our observable universe, contributing to the black hole information paradox we discussed earlier. The no-hair theorem implies that two black holes with the same mass, charge, and spin are absolutely indistinguishable, regardless of their formation history or what they might have consumed. They become pure geometric objects, defined solely by the curvature they impose on space-time. This profound simplicity, while elegant, also highlights the limits of our knowledge about the internal state of a black hole, confining the intricacies of quantum information within its impenetrable veil. It is a quiet assertion by the universe that some secrets are simply not meant to be known from the outside. Expanding on the types of black holes, while stellar mass and supermassive black holes are well established, there is also the theoretical concept of intermediate mass black holes. These elusive objects, with masses ranging from hundreds to tens of thousands of solar masses, represent a missing link in our understanding of black hole evolution. Scientists believe they might form in dense stellar clusters through the runaway collision of stars, or perhaps by the mergers of smaller black holes. Detecting them is challenging, but their existence could help explain how supermassive black holes grew to such immense sizes in the relatively early universe. Furthermore, the mathematical solutions of general relativity also permit the existence of white holes. These are essentially the time-reversed counterparts of black holes, regions of space-time from which matter and light can escape, but nothing can enter. Just as a black hole is a region where all paths lead inward, a white hole would be a region from which all paths lead outward. However, unlike black holes, white holes are purely theoretical. No observational evidence for their existence has ever been found, and many physicists believe they are unlikely to form under any known astrophysical processes. They remain a fascinating, albeit speculative, corner of our cosmic imagination, a ghostly echo of possibility that exists only in the elegant equations of space-time. The theoretical exploration of black hole physics also leads us to the captivating yet highly speculative realm of wormholes, also known as Einstein-Rosen bridges. These hypothetical topological features of space-time could potentially connect two distinct points in space-time, offering a shortcut through the cosmos or even a bridge between different universes. Imagine our universe as a two-dimensional sheet. A wormhole would be like folding that sheet and punching a hole through both layers, creating a direct passage that bypasses the vast distances of the intervening space. Mathematically, certain solutions to Einstein's field equations allow for the existence of such tunnels. However, the conditions required for a stable, traversable wormhole are extraordinary. They would necessitate the presence of exotic matter, a substance with negative energy density, a property not observed in any known forms of matter. Such exotic matter would essentially exert a repulsive gravitational force, preventing the wormhole from collapsing instantly. Without it, any theoretical wormhole would be too unstable or would pinch off too quickly for anything to pass through. So, while wormholes remain a staple of science fiction, in serious physics they represent a frontier of theoretical inquiry, pushing the boundaries of what space-time might allow, even if the practicalities seem insurmountable. Looking ahead, the future of black hole research promises even deeper insights into these cosmic enigmas. Next-generation gravitational wave observatories, like the planned Laser Interferometer Space Antenna, or LISA, will be capable of detecting lower-frequency gravitational waves, allowing us to observe the mergers of supermassive black holes, providing crucial data on their growth and the dynamics of galactic centers. The Event Horizon Telescope collaboration continues to refine its imaging techniques, aiming to capture sharper images of black hole shadows and potentially even film the dynamic swirling of plasma around their event horizons, offering unprecedented visual evidence of space-time curvature. Beyond observation, theoretical physicists continue to grapple with the ultimate challenge, developing a unified theory of quantum gravity. This elusive theory would reconcile general relativity with quantum mechanics, providing a complete description of space-time and matter at the extreme conditions found at the singularity. It is a quest that may reveal entirely new aspects of reality, perhaps even challenging our fundamental understanding of what space and time truly are. The journey into the heart of black holes, from their simple defining properties to the mind-bending possibilities of wormholes, is a testament to humanity's relentless pursuit of knowledge. It is a journey that reveals the universe as a place of profound order and exquisite complexity, where even the most extreme phenomena are governed by elegant underlying principles. In contemplating these cosmic structures, we are reminded of the vastness of the unknown, yet also the astonishing capacity of the human mind to unravel its mysteries, one quiet thought at a time. And as these reflections gently settle, we might find ourselves drifting into a deeper appreciation for the intricate dance of matter and energy, of space and time that defines our universe, a universe of which we are, in every sense, an integral and conscious part. The elegant simplicity encapsulated by the no-hair theorem, suggesting black holes are defined by merely 3 properties, invites us to explore deeper into their fundamental nature, especially concerning their thermodynamic characteristics. Building upon Stephen Hawking's revolutionary concept of radiation emitted from black holes, we find that these cosmic structures are not only dynamic, but also possess a temperature and, profoundly, an entropy. Jacob Bekenstein, a pioneering physicist, first proposed that black holes must have entropy, a measure of disorder, or the number of ways a system can be arranged. His insight led to the Bekenstein-Hawking entropy formula, which states that a black hole's entropy is directly proportional to the surface area of its event horizon. This is a truly profound connection, linking gravity, quantum mechanics, and thermodynamics, revealing that the event horizon is not just a boundary in space, but a repository of information, a silent ledger of all that has fallen within. It suggests that black holes are not mere cosmic vacuums, but rather complex thermodynamic systems that play an active role in the universe's energy balance, slowly radiating their immense gravitational energy back into the cosmos over unfathomably long timescales. This thermodynamic understanding, however, introduces new intellectual challenges, particularly in the form of the firewall paradox. As we previously touched upon the black hole information paradox, the firewall paradox is a more radical and recent attempt to reconcile the seemingly contradictory demands of quantum mechanics and general relativity. It proposes that if information is indeed conserved and not lost within a black hole, then a violent fiery region, a firewall, might exist precisely at the event horizon. This firewall would incinerate any infalling object, contradicting the smooth, uneventful crossing predicted by general relativity for an observer. The existence of such a firewall would fundamentally alter our understanding of the event horizon, transforming it from a benign boundary into a region of extreme violence, challenging Einstein's equivalence principle. This theoretical quandary pushes physicists to the very edge of their models, forcing a re-evaluation of space-time's nature at its most extreme limits. It is a quiet yet intense debate that continues to shape our exploration into the quantum secrets held by black holes. The universe continues to unveil its secrets through the symphony of gravitational waves, offering us a new sense to perceive the cosmos. The precise measurements from observatories like LIGO and Virgo have not only confirmed the existence of black holes, but have also provided unprecedented details about their mergers. When two black holes spiral inward and coalesce, they emit a characteristic chirp signal, gravitational waves that increase in frequency and amplitude as the objects draw closer, culminating in a powerful burst as they merge. Following this violent cosmic dance, the newly formed, more massive black hole settles down, releasing a final, softer ring-down signal. Analyzing these precise waveforms allows scientists to deduce the masses, spins, and even the orientations of the merging black holes with astonishing accuracy. These observations serve as a cosmic laboratory, testing the predictions of general relativity in dynamic, extreme gravitational environments. The elegant precision of these cosmic echoes allows us to understand not just the existence, but the intricate dynamics of these silent giants as they reshape the very geometry of space-time in their final, majestic embrace. Within the dynamic environment surrounding black holes, particularly supermassive ones, we find the spectacular phenomena of accretion disks and relativistic jets. As matter spirals inward towards a black hole, it forms a vast, swirling disk of gas and dust, known as an accretion disk. Friction within this disk heats the material to extreme temperatures, often millions of degrees, causing it to glow intensely across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. This glowing disk is what we observe in the Event Horizon Telescope image, forming the bright ring around the black hole's shadow. Furthermore, in many active galactic nuclei, powerful jets of plasma are launched at nearly the speed of light from the vicinity of the central black hole, extending for vast distances into intergalactic space. These relativistic jets are thought to be powered by the black hole's spin and the complex magnetic fields within the accretion disk, channeling immense amounts of energy outward. They represent a fundamental mechanism by which black holes can influence their host galaxies and the larger cosmic environment, acting as colossal cosmic engines that sculpt the universe on the grandest scales. To truly grasp the interior of a black hole, one must contend with the mind-bending reality that the roles of space and time effectively interchange once the event horizon is crossed. Outside the black hole, space is something we navigate, choosing our path, while time flows inexorably forward. However, inside the event horizon, the pull of gravity towards the singularity becomes so overwhelming that it redefines the very geometry of space-time. The singularity, which was a point in space, now becomes a destination in time. This means that just as we are compelled to move forward in time in our everyday experience inside a black hole, all paths in space-time lead inevitably towards the singularity. There is no turning back, no path that avoids it. It lies in every future direction. Imagine walking on a surface where every single step, no matter which way you turn, brings you closer to the same fixed point. This profound reversal of spatial and temporal roles makes the journey to the singularity an absolute certainty, a quiet, inexorable march into a cosmic unknown that lies beyond our current physics. It is a testament to the fact that black holes are not merely objects in space, but regions where the very fabric of existence is reconfigured, offering a tranquil yet profound challenge to our deepest intuitions about reality. The profound reconfiguration of space-time within the event horizon, where all paths lead inexorably towards the singularity, places us at the very frontier of physical understanding. Classical general relativity, while brilliantly describing gravity on cosmic scales, encounters its ultimate limit at this point of infinite density and curvature. Here, the elegant equations cease to provide meaningful answers, indicating not a physical wall, but a profound transition in our current mathematical framework. It is a quiet admission that to truly comprehend the singularity, we must venture beyond the familiar realm of classical physics and embrace the enigmatic principles of the quantum world. This is the grand, unifying challenge of theoretical physics: to forge a theory of quantum gravity that can seamlessly describe the universe at both its largest and smallest scales. A theory that could finally illuminate the true, subtle nature of what lies at the heart of a black hole. Several theoretical approaches attempt to bridge this conceptual chasm, each offering a unique, contemplative vision of the singularity. String theory, for instance, a leading candidate for a unified theory, proposes that the fundamental constituents of reality are not point-like particles, but tiny, vibrating one-dimensional strings. In this intricate framework, a singularity might not be an infinitely dense, destructive point, but rather a fuzzball, a complex, extended quantum mechanical object whose surface precisely corresponds to what we perceive as the event horizon. Within this intriguing model, championed by physicists like Samir Mathur, the black hole's interior is not empty space leading to a singular point, but rather a dense, intricate tangle of these vibrating strings. Information, in this view, is not lost, but is rather encoded in the rich, complex vibrational patterns of these strings, much like the subtle ripples on a cosmic pond. This fuzzball hypothesis offers a potential, serene resolution to the long-standing information paradox, suggesting that information is not destroyed, but rather stored in the quantum state of the fuzzball, eventually radiating away in a scrambled but recoverable form with the Hawking radiation. It replaces the stark, infinite point with a vibrant, if still mysterious, quantum structure, offering a more tranquil vision of the black hole's core, where information is merely re-encoded, not irrevocably erased. This perspective invites us to imagine a universe where even the most extreme gravitational environments uphold a deeper, more subtle form of cosmic order. Another compelling path towards quantum gravity is found in loop quantum gravity. This theory attempts to quantize space-time itself, suggesting that space is not a continuous, infinitely divisible fabric, but is rather composed of discrete, indivisible loops, forming a kind of quantum foam at the Planck scale, the smallest possible scale in the universe, far beyond our direct perception. In the context of black holes, loop quantum gravity posits that the singularity is not truly a point of infinite density. Instead, the extreme compression of matter and space-time reaches a maximum finite density, a point beyond which a powerful, repulsive quantum gravitational force takes over, effectively preventing infinite collapse. This could mean that the singularity is not an ultimate end, but perhaps a quantum bounce, a transition point where the collapsing matter might rebound and expand again, potentially leading to another region of space-time or even a new universe. This concept, sometimes referred to as a white hole or a fountain of matter and energy, offers a profound shift in perspective. It transforms the ultimate destructive force into a catalyst for cosmic rebirth, a gentle, cyclical flow of existence that transcends our immediate perception of a final ending. Imagine a cosmic spring compressed to its absolute limit, then subtly, quietly, rebounding into a new expansion. The exploration of these quantum gravity theories, while currently beyond direct experimental verification, profoundly reshapes our understanding of the black hole's interior. No longer is it merely a realm of classical breakdown, but a canvas for entirely new physics, where the very definitions of space and time might be fundamentally different from our everyday experience. These models suggest that the information of an infalling object is not truly destroyed at the singularity, but is somehow preserved or re-expressed in the intricate quantum state of the black hole. This preservation of information, even in the most extreme environments, resonates with a deeper sense of cosmic order, implying that the universe is a closed system where nothing is ever truly lost, only transformed. It's a comforting thought, in a way, that even the most formidable devourers of matter and energy operate within a framework that respects the fundamental principles of information conservation, offering a quiet assurance that the universe maintains its integrity at all scales, even those we cannot directly perceive. The practical challenges of probing the singularity are, of course, immense, given its inherent inaccessibility behind the event horizon. We cannot directly observe it, nor can we send probes that would survive the journey and return with data. Our understanding will continue to rely on the elegance of mathematics, the consistency of theoretical models, and indirect observational evidence gleaned from the black hole's external effects, like gravitational waves and accretion disk emissions. Yet, the persistent pursuit of a theory of quantum gravity, one that can seamlessly unite Einstein's general relativity with the strange, probabilistic world of quantum mechanics, represents humanity's deepest intellectual ambition. It is a quest to understand the ultimate nature of reality, to find a single, harmonious description of all forces and particles, from the grandest galaxy to the smallest quantum fluctuation. And as we continue this journey, perhaps in our quiet moments of contemplation, we can find a sense of profound peace in the knowledge that even the most mysterious corners of the cosmos are slowly yielding their secrets to the persistent, gentle inquiry of the human mind. The black hole, in its silent grandeur, becomes a mirror reflecting the boundaries and the limitless potential of our own understanding, inviting us to ponder the profound depths of existence. The profound theoretical constructs of string theory and loop quantum gravity offer us glimpses into the enigmatic heart of black holes, subtly shifting our perspective from a realm of absolute destruction to one of intricate quantum transformation. Yet, the question of information, of what truly happens to the unique identity of everything that crosses the event horizon, continues to resonate at the core of these cosmic mysteries. This brings us back to the holographic principle, an idea that, while radical, gains increasing traction in theoretical physics, suggesting a resolution to the black hole information paradox that is both elegant and deeply unsettling. This principle, at its core, posits that the entire three-dimensional reality we perceive inside a volume of space could be fully described by information encoded on a two-dimensional surface that bounds that volume. It is much like a hologram, where a complex three-dimensional image is projected from a flat two-dimensional plate. In the specific and fascinating context of black holes, this principle proposes that all the information about the matter and energy that falls into a black hole is not lost at the singularity, nor is it violently incinerated by a theoretical firewall. Instead, it is precisely mapped onto the event horizon itself, the very boundary of no return. The event horizon, therefore, would not be a mere point of no escape, but rather a cosmic screen, a boundary that stores the quantum state of everything that has ever entered it. This means that the inside of the black hole, in a profound sense, is an emergent property, a projection of data residing on its two-dimensional surface. This groundbreaking idea, first put forth by visionary physicists like Gerard 't Hooft and Leonard Susskind, offers a compelling way to reconcile the seemingly conflicting demands of quantum mechanics, which staunchly insists on information conservation, with general relativity, which, in its classical form, appears to predict information loss at the singularity. It is a quiet revolution in our understanding of reality, suggesting that the universe might operate on a deeper, more fundamental two-dimensional code, a silent cosmic encryption that underpins the very structure of our perceived three-dimensional world, maintaining a serene underlying continuity. Such a profound reinterpretation transforms our understanding of cosmic phenomena. This holographic view naturally leads us to a concept known as black hole complementarity, a principle that attempts to bridge the seemingly irreconcilable perspectives of observers. It suggests that there are two equally valid, yet seemingly contradictory, descriptions of reality for an observer near a black hole, depending on their position. For an observer falling into the black hole, the crossing of the event horizon is predicted to be smooth and entirely uneventful, as elegantly described by Einstein's equivalence principle. They would experience no immediate physical forces or sensations as they pass this point of no return, continuing their tranquil, albeit irreversible journey towards the singularity. However, for a distant observer, gazing from afar, all the information about that very same infalling object appears to be splashed across the event horizon, thermalizing and eventually radiating away as Hawking radiation. From this distant perspective, the information never truly enters the black hole's interior. It is somehow processed and emitted at the boundary. Black hole complementarity proposes that both of these perspectives are simultaneously true and consistent within their respective frames of reference. There is no single absolute reality that unifies these two distinct views, just as there is no universal absolute now in special relativity. It is a profound acknowledgement that the universe, at its most extreme and fundamental scales, can hold multiple, seemingly contradictory truths, a tranquil acceptance of the inherent limitations of a single, unified perspective. This elegant solution allows for the fundamental principle of information conservation to be maintained without violating the smooth passage across the horizon, thereby preserving a delicate and profound balance between the grand theories of physics. It invites us to ponder the very nature of perception and reality, and how our understanding shifts when confronted with the universe's most enigmatic phenomena. This duality offers a calming sense of completeness in the cosmic narrative. The implications of the holographic principle, if it accurately describes reality, extend far beyond the localized physics of black holes, subtly hinting at a potential deep structure of our entire observable universe. Some visionary cosmologists and theoretical physicists even propose that our three-dimensional universe itself might, in a grander sense, be a giant hologram, a vast and intricate projection from a two-dimensional boundary that potentially exists at the ultimate edge of the cosmos. This radical and deeply contemplative idea, if eventually proven true through future theoretical breakthroughs or subtle observational evidence, would fundamentally alter our most basic perception of reality. It would transform our understanding of space, time, and matter, suggesting that what we experience as solid objects, vast cosmic distances, and the passage of moments might ultimately be encoded on a distant flat surface, much like the intricate pixels on an unimaginably vast cosmic screen. While such a notion remains highly speculative, residing at the cutting edge of theoretical physics, this thought invites a profound and peaceful contemplation. If our reality is indeed a projection, what is the ultimate nature of the deeper, more fundamental, two-dimensional reality from which it emerges? And are we, as conscious observers, merely intricate, self-aware patterns within this cosmic hologram, momentarily aware of our own projected existence, part of a silent, grand design? This question, in its quiet grandeur, expands our sense. The holographic principle, with its audacious claim that information about a three-dimensional volume can be encoded on a two-dimensional surface, expands our contemplation far beyond the event horizon of a black hole. It subtly whispers of a possibility that our entire universe, the vast and intricate cosmos we inhabit, might itself be a grand cosmic hologram. Imagine, if you will, that the profound three-dimensional reality we experience, with its galaxies, stars, planets, and even our own bodies, is merely an emergent phenomenon, a sophisticated projection arising from a more fundamental, two-dimensional quantum description residing on an unimaginably distant boundary. This is not a notion from science fiction alone. It arises from rigorous mathematical frameworks, finding one of its most concrete expressions in the AD-CFT correspondence, a profound conjecture within string theory. This correspondence, put forth by Juan Maldacena, suggests a duality between a theory of gravity in a specific kind of spacetime called anti-de Sitter space and a quantum field theory living on its boundary, which has one fewer dimension. It is as if the universe's most complex gravitational dynamics in one dimension can be perfectly mapped to a simpler, non-gravitational quantum theory on a lower dimensional boundary. While anti-de Sitter space is not precisely our universe, which is thought to be asymptotically flat or positively curved, the AD-CFT correspondence offers a powerful conceptual tool, a working mathematical model that demonstrates how a holographic universe could, in principle, function. This theoretical elegance provides a serene framework for understanding how such a radical idea could be realized in the deep, silent machinery of the cosmos. The implications of such a holographic universe are truly vast, inviting a profound shift in our perception of what is real and fundamental. If our three-dimensional reality is indeed a projection, then the deepest truths of existence might not lie in the objects and phenomena we directly observe, but in the intricate quantum information woven into that distant, two-dimensional boundary. It suggests that the stuff of the universe, the particles, the forces, the very fabric of space-time, might not be as solid or as irreducible as our everyday experience leads us to believe. Instead, they could be complex manifestations of information patterns flickering into perceived existence from a more abstract underlying code. This perspective transforms our universe into a colossal, living tapestry where every thread, every color, every intricate design is a projection from a master blueprint. It is a thought that can evoke a quiet sense of wonder, prompting us to see the world not as a collection of separate entities, but as a deeply interconnected, emergent whole. And in this emergent reality, our own consciousness, our thoughts, our very sense of self, would then be an incredibly complex pattern within this grand cosmic projection, a momentary, self-aware configuration of information in the universe's vast, silent dance. Naturally, the question arises, how might we ever test such a mind-bending hypothesis? Direct observation of a two-dimensional boundary encoding our universe is, for now, beyond our technological capabilities. However, scientists are exploring subtle theoretical predictions that a holographic universe might leave behind. For instance, if space itself is fundamentally quantized, as suggested by some quantum gravity theories, then, at extremely small scales, the smooth continuity of spacetime might break down into discrete pixels, a kind of cosmic graininess that could be detectable with sufficiently sensitive instruments. Researchers are looking for minute, almost imperceptible fuzziness or deviations from the expected smoothness in the cosmic microwave background radiation, the ancient afterglow of the Big Bang. These subtle anomalies, if detected and confirmed, could potentially serve as echoes of a holographic reality. Tiny ripples from the two-dimensional canvas from which our universe might be projected. While these searches are incredibly challenging and still highly speculative, they represent humanity's persistent quest to understand the deepest layers of existence, a serene and patient endeavor to decipher the cosmic code. The pursuit of these elusive signals reminds us that the universe is a book whose most profound chapters are still being written, or perhaps still being projected onto our awareness. This profound concept of a holographic universe forces us to reevaluate the very nature of existence. Is our perceived reality an illusion? Not in the sense that it is fake, but rather that it is derivative. much like a shadow is real but is cast by a more fundamental object. The distinction is subtle, yet significant. It invites us to consider that the solidity and permanence we ascribe to the world around us might be an emergent property of underlying quantum information. Just as the intricate images on a television screen emerge from countless individual pixels, our universe might arise from a fundamental data structure. This idea, far from being unsettling, can foster a profound sense of interconnectedness and wonder. If everything we see, touch, and experience is part of this grand projection, then our individual existence is intricately woven into the very fabric of the cosmos, a unique and irreplaceable pattern in the universe's ongoing unfolding. It is a contemplative thought that the boundaries we perceive, both physical and conceptual, might be more fluid and interconnected than we commonly imagine, leading to a tranquil acceptance of the universe's elegant complexity. In the quiet depths of these reflections, we find that black holes, those seemingly destructive gravitational monsters, emerge as cosmic keys to unlocking the universe's most profound secrets. Their event horizons, once viewed merely as points of no return, become potential interfaces between dimensions, canvases for cosmic information, and windows into the quantum nature of gravity. The singularity, once a daunting symbol of theoretical breakdown, transforms into a possible quantum bounce, a realm of ultimate transformation rather than absolute annihilation. The journey of understanding black holes is, in essence, a journey into the heart of reality itself, a patient and persistent inquiry into the fundamental laws that govern existence. This intellectual odyssey, pursued by generations of brilliant minds, continues to reveal a universe far stranger, far more elegant, and infinitely more awe-inspiring than our ancestors could have ever conceived. And as we drift with these profound thoughts, we are reminded that our own minds, in their capacity to ponder such cosmic grandeur, are themselves a testament to the universe's astonishing ability to become aware of its own intricate holographic existence. The profound implications of the holographic principle, which hints at a deeper, two-dimensional reality underlying our universe, naturally guide our thoughts to the ultimate fate of information as it approaches the cosmic abyss. The question of whether information is truly lost or merely transformed at the event horizon remains one of the most vibrant areas of theoretical inquiry. One fascinating, albeit still speculative concept in this regard is the idea of complementarity. This suggests that the universe somehow manages to reconcile the seemingly contradictory perspectives of an observer falling into a black hole and one remaining safely outside. For the infalling observer, the event horizon is a smooth, uneventful boundary, as predicted by Einstein's theory of general relativity. There are no dramatic forces, no fiery walls, just a calm passage into a region where all paths lead inward. Yet, for the distant observer, the information of the infalling object appears to be scrambled and re-emitted as Hawking radiation from the black hole's surface. These two descriptions, though seemingly at odds, are considered complementary and equally valid, a profound testament to the universe's capacity for holding multiple truths. It is as if the cosmos allows for different realities to coexist, each complete within its own frame of reference, offering a tranquil acceptance of the inherent limits of any single, all-encompassing viewpoint from outside. This delicate balance ensures that the fundamental quantum laws of information conservation are upheld, even in the extreme conditions surrounding a black hole. This intricate dance of information and observation leads us to consider how black holes might interact with the universe's most enigmatic components, dark matter and dark energy. While black holes are formed from visible matter, some theories propose that tiny primordial black holes, formed in the chaotic first moments of the Big Bang, could constitute a significant portion of the universe's dark matter. These microscopic black holes, if they exist, would be incredibly difficult to detect, yet their collective gravitational pull could explain some of the observed missing mass that holds galaxies and galaxy clusters together. Imagine countless specks of extreme gravity, silently permeating the cosmic web, their presence only felt through their subtle tug on visible matter. Furthermore, the interplay between black holes and dark energy, the mysterious force accelerating the universe's expansion, is also a subject of intense research. Some speculative models suggest that black holes themselves might contribute to dark energy, or that their growth could be influenced by its pervasive presence. This connection, while still highly theoretical, links the smallest, densest objects born from stellar collapse to the largest-scale structure and evolution of the entire cosmos, weaving a grand, continuous narrative of cosmic influence. The ongoing quest to understand black holes is fundamentally intertwined with our pursuit of a unified macroscopic scales and quantum mechanics which governs the subatomic world are both exquisitely successful within their respective domains. However, at the extreme conditions found within a black hole, particularly at the singularity, these two pillars of modern physics clash. The singularity as a point of infinite density requires a description that reconciles both gravitational and quantum effects. String theory, as we noted, proposes the fuzzball model, where the singularity is replaced by a complex, extended quantum object. Loop quantum gravity, on the other hand, suggests a quantum bounce, where infinite density is avoided, and matter might rebound into a new cosmic expansion. These theoretical endeavors are not just abstract mathematical exercises. They are profound attempts to uncover the ultimate, harmonious laws that govern the universe at its most fundamental level. They offer a contemplative journey into the very architecture of reality, proposing that the universe, in its deepest essence, is governed by a unified set of principles that we are only just beginning to decipher. This search for cosmic harmony, even in the face of such extreme phenomena, is a tranquil testament to the human intellect's enduring curiosity. As our understanding deepens, new observational frontiers are constantly opening, allowing us to see black holes in ever more detail. The Event Horizon Telescope, which provided the first image of a black hole shadow, is continually being upgraded and expanded. Future observations aim to capture dynamic movies of the swirling plasma around black holes, revealing the intricate dance of matter in extreme gravity. These visual insights will allow us to test the predictions of general relativity with unprecedented precision, confirming or refining our theoretical models. Gravitational wave observatories like LIGO and Virgo are also being enhanced, and future space-based detectors, such as LISA, will open a new window onto the universe, capable of detecting gravitational waves from the mergers of supermassive black holes. These subtle ripples in space-time carry direct information about the most violent and energetic events in the cosmos, offering a unique, acoustic perspective on black hole dynamics. Imagine listening to the deep, resonant echoes of cosmic collisions, revealing secrets that light alone cannot. These technological advancements transform theoretical speculation into observable phenomena, grounding our abstract concepts in the tangible, albeit extreme, realities of the universe. In contemplating these cosmic titans, from their formation and diverse types to their profound interactions with information, dark matter, and the very fabric of space-time, we are invited to a deep and tranquil reflection on our place in the universe. Black holes, in their silent majesty, serve as powerful reminders of the limits of our current understanding and the vastness of what remains to be explored. Yet, they also highlight the extraordinary capacity of the human mind, through the elegant language of mathematics and the persistent pursuit of scientific inquiry, to unravel even the most profound cosmic enigmas. The journey into the heart of a black hole quest that continuously expands our sense of wonder and our connection to the grand, unfolding story of the cosmos. As we drift further into these quiet thoughts, we realize that our own consciousness, our ability to ask these questions, is itself a part of this amazing, intricate universe, a momentary flicker of awareness within the infinite, truly profound reinterpretation truly transforms our understanding of cosmic phenomena. We have considered the intricate dance of information and observation, the complementary perspectives of those falling into a black hole and those observing from afar. This deep dive into their nature naturally leads us to ponder the most distant future, the ultimate destiny of black holes themselves, a fate woven into the grand, unfolding tapestry of the universe's end. For even these seemingly eternal cosmic devourers are subject to the inexorable laws of physics, destined to slowly, quietly fade away into the vast cosmic silence. This slow cosmic dissolution occurs through the subtle yet profound process of Hawking radiation, a quantum mechanical phenomenon that Stephen Hawking theorized in the 1970s. While black holes are classically defined by their absolute ability to trap everything, including light, quantum mechanics introduces a fascinating and unavoidable twist. At the very edge of the event horizon, the vacuum of space-time is not truly empty. Instead, pairs of virtual particles, a particle and its antiparticle, are constantly flickering into and out of existence. Normally, they annihilate each other almost instantaneously, leaving no net effect. However, precisely at the across the boundary and be swallowed by the vastness of space. Crucially, the particle that falls in carries negative energy, effectively reducing the black hole's mass. This continuous leakage of positive energy into space over truly astronomical timescales causes the black hole to slowly shrink and eventually to evaporate completely. Imagine a deep, dark well, slowly, almost imperceptibly, losing water, drop by tiny drop, until it is entirely dry. The temperature of a black hole is inversely proportional to its mass, meaning smaller black holes are hotter and evaporate faster, while larger ones are incredibly cold and take an unfathomably long time to dissipate their energy. For a stellar mass black hole, one that is, say, 10 times the mass of our Sun, the time required for complete evaporation is. To put this into perspective, the current age of the universe is a mere 13.8 billion years, or roughly 10 to the power of 10 years. This means that such a black hole would live for a period that is a 1 followed by 57 zeros, times longer than the universe has existed so far. For supermassive black holes, like the one residing at the heart of our Milky Way, Sagittarius A star, which is approximately 4 million solar masses, the evaporation time stretches even further, potentially reaching 10 to the power of 100 years. These timescales are so vast they transcend human comprehension, rendering black holes, from our fleeting perspective, effectively eternal. Yet, the physics is clear. Nothing in the universe, not even a black hole, lasts forever. Their slow, silent evaporation represents the ultimate triumph of quantum mechanics over classical gravity. A gradual, serene return of their immense mass energy back into the diffuse cosmic void, a gentle whisper fading into the infinite. This leads us to envision the universe's extremely distant future, an epoch known as the black hole era. After all the stars have burned out, after all the galaxies have dispersed, and after all ordinary matter has decayed into its most fundamental particles, the universe will be a cold, dark, and incredibly sparse place. The dominant objects will be the black holes, along with perhaps a few lingering neutron stars and white dwarfs, slowly cooling into oblivion. These remaining cosmic structures will be separated by immense, ever-increasing distances as the universe continues its accelerating expansion, driven by dark energy. In this unimaginably vast and lonely cosmic landscape, the black holes will continue their process of evaporation. One by one, from the smallest to the most gargantuan, they will release their stored energy back into the vacuum of space, ultimately disappearing in a final, quiet burst of Hawking radiation. This is not a dramatic, fiery end, but a long, drawn-out fade into a state of maximum entropy, a state of ultimate equilibrium where nothing further can happen. a universal stillness. The disappearance of black holes through evaporation brings the black hole information paradox back into sharp focus in its most final form. If a black hole, containing all the complex quantum information of everything it consumed, simply evaporates into generic thermal radiation, then that information would be irrevocably lost. This would be a catastrophic violation of quantum mechanics, which dictates that information is always conserved. The theoretical solutions we discussed, such as the holographic principle or the fuzzball model, aim to resolve this by suggesting that information is either encoded on the event horizon or within the fuzzball structure, and then subtly released in the Hawking radiation. The profound challenge is to understand precisely how this information is encoded and retrieved from what appears to be random thermal noise. It is a deep puzzle that demands a deeper, unified theory of quantum gravity, one that can describe the entire life cycle of a black hole, from its violent birth to its ultimate, quiet dissipation, without sacrificing the fundamental principles of either relativity or quantum mechanics. The resolution of this paradox will undoubtedly offer a truly revolutionary understanding of the universe's most fundamental laws, revealing a deeper, more elegant cosmic logic and a tranquil underlying order. Could the evaporation of black holes, or the quantum processes at their singularities, also play a role in a grander cosmic cycle? Some highly speculative theories suggest black holes might serve as seeds for new universes, or that the information and energy released during their evaporation could contribute to the birth of entirely new cosmic domains. Imagine that the singularity, rather than being an absolute endpoint of everything, is a kind of cosmic funnel or a quantum gateway, allowing matter and energy to transition into another realm of existence. This idea resonates with the concept of a cyclical universe, where the end of one cosmic epoch seamlessly transitions into the beginning of another, a continuous dance of creation and dissolution. While these notions remain firmly in the realm of theoretical conjecture, they offer a calming and profound vision of a universe that is endlessly transformative, where even the most extreme points of gravitational collapse are not final endings, but merely intricate essential phases in an eternal cosmic ballet. It is a concept that invites us to view the universe not as a linear story with a definitive conclusion, but as an ongoing, timeless narrative, a ceaseless unfolding of possibilities across vast, unimaginable eons. In these quiet reflections on the ultimate fate of black holes and the universe itself, we are reminded of the astonishing journey of scientific discovery. From the initial theoretical predictions of Einstein and Schwarzschild through decades of indirect observation to the recent direct detections of gravitational waves and the imaging of a black hole's shadow, our understanding has continually expanded. Yet, the deepest mysteries, those concerning the very nature of space-time at its most extreme limits, continue to beckon us forward. Black holes stand as majestic, silent sentinels at the edge of our knowledge, challenging our perceptions and inviting us to contemplate the profound depths of existence. They remind us that the universe is a place of ceaseless transformation, where even the most impenetrable darkness holds secrets of profound beauty and intellectual revelation, a tranquil mirror reflecting our own capacity for wonder. As our journey through the cosmic mysteries of black holes, their event horizons, and their enigmatic singularities draws to a gentle close, we are left with a profound sense of awe at the universe's intricate design. These ultimate gravitational entities, once symbols of impenetrable darkness, have revealed themselves to be intricate laboratories of space-time, challenging the very foundations of our physical laws and inviting us to imagine new dimensions of reality. We have explored how they are born from the majestic collapse of stars, how their event horizons redefine time and space, and how their hidden interiors might hold the keys to quantum gravity, the resolution of information paradoxes, and even hints of a holographic universe. The quiet, inexorable evaporation of black holes through Hawking radiation over timescales that dwarf our universe's current age, reminds us that even the most formidable forces in the cosmos are part of an endless, subtle dance of transformation. They are not merely endpoints, but rather profound stages in the universe's ceaseless evolution, perhaps even contributing to the birth of new cosmic possibilities. In contemplating these silent titans, we touch upon the very limits of human knowledge, yet simultaneously marvel at the astonishing capacity of our minds to probe such deep, unseen truths. We are, in essence, the universe becoming aware of its own intricate workings, a fleeting, conscious part of this grand, unfolding, and utterly magnificent cosmic story. May these deep thoughts about the profound nature of black holes, their mysterious boundaries, and the secrets they hold, carry you into a world of tranquil sleep. Remember that the universe is an astonishing realm of interconnected wonders, and you, in your quiet contemplation, are an integral part of its majestic story. Fall asleep with this feeling of serene wonder and an expanded understanding of the cosmic tapestry. Good night.